The universe is supposed to follow rules, laws of physics, patterns of behavior, things we can understand. But the more we look, the more we find things that simply don't make sense. Strange planets that shouldn't have formed, stars that live longer than they should, galaxies that break the rules, and cosmic puzzles that leave scientists scratching their heads. It's as if the universe likes to surprise us, reminding us that we still have so much to learn. Some of these mysteries have possible answers. Others seem to break the rules entirely. Carbon-rich diamond exoplanets, the case of 55 Cancri E. In the search for worlds beyond our solar system, scientists have found planets so different from our own that they almost seem like they belong in another reality. One such discovery is 55 Cancri E, a planet that orbits a nearby star in the constellation of Cancer. At first, 55 Cancri E appeared to be just another rocky planet, similar in size to Earth, but orbiting much closer to its star. As astronomers looked closer, though, they realized that this planet might be far more exotic, a world made largely of carbon and possibly deep within, filled with diamond. When scientists first measured 55 Cancri E, they noted two important things: its size and its mass. Size tells you how big the planet is. Mass tells you how much stuff is packed inside it. With these two numbers, you can calculate density, which gives clues about what the planet might be made of. 55 Cancri E was denser than Earth, but not by an amount that could be easily explained by the materials we are used to. Earth is mostly made of silicate rocks and iron, a mixture that gives it a certain expected density. But 55 Cancri E seemed too dense for that typical recipe, leading scientists to suspect that its interior must be built from something else. At first, researchers considered the possibility that it had a massive iron core, far larger than Earth's, but that idea didn't quite fit all the observations. Another idea started to take shape, that maybe 55 Cancri E was made from an entirely different mix of elements. Maybe instead of being rich in oxygen and silicon like Earth, this planet was rich in carbon. If the early building blocks of 55 Cancri E were loaded with carbon instead of oxygen, the minerals and rocks that formed would be completely different. Instead of silicates, they might be carbides, compounds of carbon and metals. And under the right pressures deep inside the planet, carbon itself could crystallize into diamond. In our solar system, most planets formed from a cloud of gas and dust that had a lot of oxygen relative to carbon. That chemistry favors silicate minerals, which dominate Earth, Mars, Venus, and Mercury. But in a different system, with a different balance of elements, a planet like 55 Cancri E could emerge, one where carbon rules instead of oxygen. Once proposed, this idea began to make sense of the planet's strange properties. The parent star of the planet, called 55 Cancri A, has a higher ratio of carbon to oxygen than the Sun. If the material that formed the planet came from a carbon-rich environment like this, then it would explain why the planet turned out so differently. In such a disk, instead of silicate rocks forming first, carbon compounds would dominate the early solid materials. Over time, these would merge and grow into a planet with a very different interior, one filled with graphite, silicon, and carbide. The outer layers of 55 Cancri E might be made of graphite, the same material found in pencils. Deeper down, under immense pressure, graphite would transform into diamond, just as it does deep inside the Earth, but on a far greater scale. Instead of a diamond core being a small feature, as it might be on Earth, it could make up a large fraction of the planet's entire mass. The evidence is indirect, built from measurements of mass, radius, density, and the chemistry of the star. Still, the match between the theory and the observations is strong enough that many scientists consider the diamond planet model a leading explanation for 55 Cancri E's strange character. Diamond is incredibly strong and has very different physical properties than the regular rocks we see on Earth. A landscape made largely of diamond would reflect light differently. It would feel different underfoot. Mountains could rise taller without crumbling under their own weight. It orbits its star very closely, completing a full orbit in just about 18 hours. That means it is extremely hot. Daytime temperatures could soar above 2,500 degrees Celsius. This heat rules out any hope of a cool, sparkling surface of exposed diamond. The extreme conditions likely cause the surface to melt or vaporize, creating a harsh and volatile environment. Some studies even suggest that the planet's surface might be covered by a deep ocean of molten rock or a thick atmosphere of superheated gases. Its existence shows that when the ingredients and conditions are right, nature can build planets in ways we never would have predicted. The carbon-rich nature of 55 Cancri E hints that there could be many more exotic worlds out there, shaped by chemistry completely unlike anything we know from home. Superpuff exoplanets, inflated low-density worlds beyond expectation. While planets like 55 Cancri E show us how strange a planet's interior can be, there is another group of exoplanets, the so-called superpuffs, that are so light and airy that their densities are lower than anything scientists ever expected to find. Instead of being made of diamond or metal, these planets are more like giant balls of cotton candy floating through space. Using the transit method, where a planet passes in front of its star and blocks a little bit of light, scientists can measure how big a planet appears. Some planets, they found, were nearly the size of Jupiter, the largest planet in our solar system. But when they measured their masses, using the tiny gravitational tug the planets exert on their stars, something didn't add up. These huge-looking planets had only a fraction of Jupiter's mass. In fact, some were only a few times more massive than Earth. When you combine a large radius with a small mass, you get an extremely low density. And in the case of superpuffs, the densities are almost unbelievably low, even lower than water, lower than wood, lower even than cotton candy. Some of these planets have densities less than 0.1 grams per cubic centimeter. To put that in perspective, Earth's average density is about 5.5 grams per cubic centimeter. Even Saturn, the least dense planet in our solar system, is still much denser than these superpuffs. How could a planet be so big and yet so light? The answer seems to lie in their enormous, bloated atmospheres. Instead of being made mostly of rock or ice, these planets are wrapped in thick, extended envelopes of hydrogen and helium gas. These gases are very light, but they take up a lot of space. If a planet has a large enough atmosphere made mostly of hydrogen and helium, it can appear much larger than its rocky or icy core would suggest. But this leads to new puzzles. Hydrogen and helium are very easy to lose, especially when a planet is close to its star. High-energy radiation from the star can strip away the outer layers of gas over time. This process, called atmospheric escape, should cause a lightweight planet to shrink. Yet some superpuff planets are found orbiting fairly close to their stars, where this stripping should be strongest. It's a mystery how they can hold on to their bloated atmospheres. One idea is that these planets might be younger than we think, caught during a brief early phase of their lives before their atmospheres shrink. Another idea is that they somehow have magnetic fields or other protective features that help shield them from their star's radiation. Or maybe they formed far from their stars, where its cold and atmospheric loss is slower, and then migrated inward later. Superpuff planets have been found in several different systems. One of the best-known examples comes from the Kepler-51 system, located about 2,600 light-years from Earth. Kepler-51 has at least 3 planets that are extreme examples of the superpuff type. These planets are each about the size of Jupiter, but have masses just a few times that of Earth. Their densities are so low that if you could somehow place them in a giant bathtub of water, they would float. And not just float, but bob high above the surface like a piece of cork. Their thick atmospheres should, in theory, be easier to analyze because there's more gas for light to pass through. But at the same time, these atmospheres may be filled with clouds and hazes that block or scatter light, making it harder to see their chemical signatures. In some cases, these hazes could be made of complex hydrocarbons, a little like the smog that forms in Earth's cities, but far thicker and covering the entire planet. If the clouds are thick enough, they can hide the deeper parts of the atmosphere from view, leaving scientists with frustratingly flat, featureless signals, when they try to study the planets with tools like the Hubble Space Telescope. Newer telescopes, such as the James Webb Space Telescope, or JWST, might be able to see through the haze and reveal more about what these planets are really like. In the early life of a solar system, young planets are often surrounded by thick gas disks. If a small rocky core forms early enough, it can pull in a large amount of gas before the disk disappears. But if it forms too late, the gas will already be gone, and the planet will stay small and rocky, like Earth or Mars. Superpuffs might be the leftovers of this early gas-rich phase, giving us a glimpse of how young planets look before they settle into more stable forms. Another idea is that some superpuffs are actually small, icy worlds that formed far from their stars, where the materials needed to build rocky planets were scarce. These icy worlds could build thick atmospheres from gases released by their interiors or picked up from the surrounding disk, and if they later migrated closer to their stars, the heat could cause their atmospheres to swell even further. Can a planet this airy survive for billions of years? If they do survive, do their atmospheres eventually shrink and transform them into more typical types of planets, like mini-Neptunes or super-Earths? Or do they somehow hold on to their fluffy nature indefinitely, becoming a class of planets unlike anything in our solar system? Some surveys suggest that small puffy planets are fairly common around other stars, although extreme cases like Kepler-51's planets are still rare. It could be that a wide range of young planets go through a puffy stage early in their lives, only to shrink later as they lose mass. Some worlds turn into glittering stones forged in extreme pressures. Others inflate into ghostly, oversized balloons drifting around their stars. The universe, it seems, has far more ways of building planets than we ever dreamed. And as we continue to search, it is certain that even stranger worlds await, hidden in the light of distant suns. Cathonian planets, evaporated remnants of once majestic gas giants. The idea of Cathonian planets comes from observations of hot Jupiters, the giant planets found orbiting extremely close to their stars. These hot Jupiters are huge, about the size of Jupiter or bigger, but they orbit so close to their stars that a single year lasts only a few Earth days. At such short distances, the planets are exposed to intense heat and powerful streams of charged particles from their stars, conditions that would be deadly to a planet's atmosphere. When astronomers looked closer at some of these hot Jupiters, they began to realize that the planets were losing mass. Their atmospheres were evaporating into space, blown away by the energy pouring out from their stars. As the gas is stripped away, what remains is the dense, rocky or metallic core that once sat deep inside the giant planet. This core, once hidden under thick layers of hydrogen and helium, is now exposed to space. It continues to orbit close to its star, enduring intense heat, but now as a much smaller, denser, and very different type of planet. This is a Cathonian world, named after the ancient Greek word Cathonic, meaning of the underworld. Cathonian planets are difficult to confirm directly because the process that creates them takes a very long time. But some candidates have been identified. Astronomers look for small, dense planets in orbits where it would be unlikely for a planet to have formed without some special process. In other words, they find planets where a gas giant could once have existed, but where only a rocky remnant remains today. One well-known example is the planet Corot 7b. This planet is about 70% larger than Earth, but orbits its star so closely that a year lasts only about 20 hours. Surface temperatures are estimated to be over 2,000 degrees Celsius. Some scientists think that Corot 7b might be the core of a former gas giant that lost its atmosphere long ago. If so, it would be a Cathonian planet, the first of its kind ever found. Another potential example is the planet WASP-12b, a hot Jupiter currently in the process of losing its atmosphere to its star. Observations have shown a large cloud of gas trailing behind the planet like a comet's tail. Over time, if this escape continues, the planet could eventually lose most or all of its gaseous envelope. In our solar system, planets like Earth and Jupiter have been relatively stable for billions of years. But in other solar systems, where planets orbit much closer to their stars, life can be far harsher. A planet that once stood as a giant can be whittled down to a shadow of its former self, left to bake under the relentless glare of its sun. The transformation from gas giant to Cathonian planet is a slow death, happening over relatively long periods of time. The process begins with the outermost layers of the atmosphere, where hydrogen atoms are heated until they move fast enough to escape the planet's gravity. As more and more gas is lost, the atmosphere shrinks. The planet's radius decreases, but its mass stays mostly the same at first, because the atmosphere, while large, is not very heavy compared to the rocky core inside. As the atmosphere continues to erode, more substantial layers are stripped away. The planet becomes smaller and denser over time, eventually reaching a point where little or no gas is left. What remains is a planet made of rock, metal, and other heavy elements, a far cry from the towering ball of gas that once traveled through space. With no thick atmosphere to protect it, the surface would be bombarded directly by radiation from the star. The heat would keep the rocks molten or semi-molten in many cases. The planet might even have a thin atmosphere made not of gas, but of vaporized minerals, creating a wispy cloud of heavy elements like sodium, magnesium, and iron surrounding it. Cathonian planets show what happens when planets migrate inward toward their stars and are then shaped by their new environments. They also help explain some of the gaps seen in the distribution of exoplanet sizes. For example, there seems to be a radius valley, a noticeable lack of planets of certain sizes in certain orbits. Cathonian planets could help explain part of that missing population, as gas giants lose mass and shrink into smaller worlds. In the early days of planetary science, it was often assumed that planets formed and then simply stayed the way they were. Now it is clear that stars can play an active role in changing, shaping, and even destroying the planets that orbit them. A star's heat, light, and winds can sculpt its planetary system just as surely as gravity does. How common are such planets? How long does it take for a gas giant to be stripped down to its core? What happens to the remnants? Do they continue to erode until nothing is left? Or do they find a kind of new stability as scorched but enduring rocky worlds? Future observations will need to answer these questions, especially by looking for planets around older stars where this process would have had time to complete. Extreme eccentricity worlds, Goldilocks zones that come and go. While some planets are transformed by the stars they orbit, others are shaped by the paths they take through space. Among the strangest examples are the planets that follow extremely eccentric orbits, long stretched-out loops that carry them swinging wildly between their star's hottest and coldest zones. In most solar systems we know, planets move along paths that are nearly perfect circles. Earth's orbit, for example, is only slightly elliptical, meaning the difference between the closest and farthest points from the Sun is small. This steady path is one reason why Earth's climate has been relatively stable for billions of years, allowing life to develop and survive. But not all planets are so lucky. Some exoplanets move in orbits so stretched out that they spend part of their year freezing in the cold outer parts of their systems and part burning under the intense heat of their stars. These extreme orbits can make a planet's environment swing between conditions that are wildly different, from temperatures where water would freeze solid to temperatures where any atmosphere could boil away. A planet like this might pass through the so-called Goldilocks zone, the region around a star where conditions might be just right for liquid water, but only for a short time during each orbit. For the rest of its journey, it would probably be too cold or too hot for life. Astronomers measure the shape of a planet's orbit with a number called eccentricity. A perfect circle has an eccentricity of 0. An orbit like a long oval has an eccentricity closer to 1. Some exoplanets, like HD 80606b, have eccentricities as high as 0.93. This planet, a gas giant 4 times the mass of Jupiter, takes 111 days to complete one orbit around its star. But it spends most of that time far from the star, in deep space, and then dives in close during a brief, intense flyby that heats its atmosphere by hundreds of degrees in a matter of hours. When the planet is far from its star, its atmosphere cools and contracts. But as it swoops inward, the temperature spikes rapidly, causing the atmosphere to puff up and shift. Storms may rage across the planet, driven by the sudden influx of heat. Winds could reach thousands of kilometers per hour. The whole world is shaken by a sudden, violent summer that lasts only a short time before the planet moves back out into the cold. For rocky planets, the consequences of such orbits could be even more extreme. Imagine a planet similar to Earth, but with a highly eccentric orbit. For part of its year, the planet might be frozen, with icy oceans and snow-covered continents. Then, over a few short weeks or months, it would swing inward toward its star. Temperatures would soar, ice would melt. Water might become liquid for a short time. Plants, if they ever evolved, would have to survive brutal seasons unlike anything seen on Earth. Animals would need to adapt to long periods of deep freeze, followed by sudden scorching heat. Stable climates help ecosystems grow and evolve. On Earth, even during ice ages, the basic structure of seasons and climates remained somewhat predictable. But on a world with an extreme eccentric orbit, predictability would be hard to come by. Every year would bring drastic changes. Life might only be possible during the brief window when the planet passes through the Goldilocks zone. And even then, only for organisms able to grow and reproduce quickly during the short time available. Perhaps life on such planets would need to hibernate, lying dormant during long periods of extreme cold or heat, waking only when conditions briefly become favorable. Microbes on Earth can do this, forming spores or cysts that survive harsh conditions for years or even decades. If life could evolve such resilience, it might survive on an eccentric world, despite the brutal challenges. Extreme eccentricity might not be just a feature of gas giants and rocky planets. It could also affect moons. A large moon orbiting an eccentric planet would experience complicated changes in heat, tides, and radiation levels over the course of each orbit. The gravitational pull between the moon and its planet could also generate internal heat, possibly keeping subsurface oceans warm even when the moon is far from the star. Astronomers think that highly eccentric orbits can be created in several ways. Sometimes they are the result of gravitational battles between planets. If two large planets form near each other, their mutual pulls can distort their orbits over time, stretching them out of shape. Other times, a passing star or a distant companion star can tug on a planet's orbit, causing it to become elongated. Once an orbit becomes highly eccentric, it can stay that way for billions of years unless another event occurs to smooth it out. Finding planets with extreme eccentricities is not easy. Many detection methods, like the transit method, work best when orbits are regular and predictable. Radial velocity methods can detect eccentric orbits, but it takes careful observations over long periods to map the full shape of the orbit. As a result, we may only be seeing a small part of the true population of eccentric worlds. Traditional views of the habitable zone picture a stable, ring-shaped region around a star, where a planet can orbit comfortably and maintain liquid water. But eccentric planets show that habitability can be more complicated. A planet might pass through the habitable zone for only a few weeks or months each orbit. Could life survive under these conditions? Could intelligent life evolve on a world where the environment swings so violently from one extreme to another? For now, most scientists think that stable Earth-like planets offer the best chances for complex life. But that doesn't mean eccentric worlds are sterile. Life on Earth has shown incredible flexibility, surviving in boiling hot springs, frozen tundras, and even deep underground. It is possible that somewhere in the galaxy, life has found a way to adapt to the wild seasons of an eccentric world. In a universe filled with endless variety, extreme eccentricity planets are a reminder that not all worlds are calm and steady like our own. Some live on the edge, swinging between fire and ice with every passing year, through cycles of intensity and calm, over and over, for eons. The Pistol Star's enigmatic wind, mass loss beyond all models. Deep in the crowded heart of the Milky Way lies the Pistol Star, named for the shape of the nearby Pistol Nebula, which it is believed to have helped create. Bright, massive, and intensely powerful, the Pistol Star is not just notable for its size or its brightness. It is best known for its incredible and seemingly impossible rate of mass loss. The winds blowing from this star are so strong and so thick that they defy nearly everything that models of stellar physics have predicted. The Pistol Star was first brought to attention in the 1990s, when astronomers, using infrared observations, were able to peer through the heavy clouds of gas and dust that usually hide the galaxy's center. What they found was astonishing. The Pistol Star appeared to be one of the most massive and luminous stars ever discovered, with an initial mass that might have reached as high as 200 times that of our Sun. Even more surprising, it had already shed a large part of that mass into space, forming an expanding shell of gas and dust that glowed faintly around it. Normally, stars lose mass through processes like stellar winds or eruptions over long periods. The Sun, for example, loses a tiny amount of its mass every year through a slow solar wind. Even the most massive stars, while shedding material more quickly, tend to do so within certain expected limits. Stellar models have long predicted that radiation pressure, light itself pushing against matter, can drive material away from a star. But there was always an assumed upper boundary to how much mass could be lost without disrupting the star's stability entirely. The Pistol Star seems to have crossed that boundary. Observations suggest it has lost at least 10 solar masses of material in just a few thousand years, a blink of an eye on cosmic timescales. Its current winds are thought to carry away material at a rate of about 10 million times the mass loss rate of the Sun. What makes this even more intriguing is that the Pistol Star is still relatively young, probably less than 2 million years old. Massive stars live fast and die young, but the Pistol Star's short lifespan does not fully account for the amount of material it has already cast off. Something more intense and violent must be happening in its outer layers. Astronomers have proposed several possible explanations. One idea is that the Pistol Star is undergoing what is known as a luminous blue variable, or LBV phase. LBVs are massive stars that experience brief but extreme periods of instability. During these episodes, they can throw off large amounts of material in sudden outbursts, sometimes triggered by changes deep within their cores or by complex interactions between radiation and gas. Famous examples of LBVs include Eta Carinae, another massive star known for its dramatic outbursts. However, even compared to other LBVs, the Pistol Star seems extreme. Its mass loss rate is not just high, it is orders of magnitude above what is seen even in violent LBV phases elsewhere. This raises questions about whether another, less understood process might be at work. One possibility is that the intense environment of the galactic center plays a role. The central regions of the Milky Way are filled with strong magnetic fields, dense clouds of gas, and turbulent interactions between stars. It is possible that these environmental factors have enhanced the star's natural wind, stripping material away faster than would happen in a quieter region of space. Alternatively, the Pistol Star might have had an unusual beginning, forming through the merger of two already massive stars. Such a merger could leave behind a highly unstable object prone to rapid mass loss. Massive stars like it do not live long under the best of circumstances. With so much mass being lost so quickly, the star's fate could be even stranger than usual. It might end its life as a pair instability supernova, an extremely rare type of explosion where the entire star is ripped apart without leaving behind a black hole or neutron star. Or, if it manages to hold onto enough mass, it could collapse into a massive black hole, adding to the population of black holes thought to lurk near the galaxy's center. The material shed by the Pistol Star is also important for the environment around it. The gas and dust it has thrown into space enrich the interstellar medium with heavier elements, helping to seed the formation of new stars and planets. In this way, the Pistol Star's violent winds contribute to the ongoing cycle of birth, death, and rebirth that shapes galaxies over billions of years. Studying the Pistol Star is not easy. It lies behind thick curtains of dust that block visible light, meaning most observations must be made in the infrared or radio wavelengths. Even then, teasing out details about the star's exact mass, temperature, and composition is challenging. The surrounding nebula, made up of the material the star has already lost, adds another layer of complexity. But these challenges also make the Pistol Star valuable for developing new techniques and expanding the limits of our knowledge. High-resolution imaging from newer telescopes could reveal finer details of the outflowing material, while advanced spectroscopy could help pinpoint the chemical fingerprints of the winds and the processes driving them. In a galaxy filled with strange and powerful objects, the Pistol Star stands out for the sheer scale of its loss. Its intense winds force astronomers to rethink what is possible for the most massive stars. In the universe's most extreme corners, nature often finds ways to outpace human expectations. Whether it explodes in a brilliant final outburst or slowly fades as it sheds the last of its mass, it will leave behind a mark on its surroundings and on our understanding of how stars live and die. Ultra-hot Jupiters with thermal inversions, flipped atmospheric models. On Earth, and on most planets and moons with atmospheres, the air gets colder as you move upward through the atmosphere. Near the surface, sunlight warms the ground, and in turn the ground warms the air just above it. As you go higher, away from this source of heat, the air becomes cooler. This simple pattern is one of the basic rules of how atmospheres work, or at least that is how it once seemed. Ultra-hot Jupiters can complete an orbit in just a few days, or even less, and they are locked into a kind of gravitational grip, showing the same face to their star at all times, much like how the Moon always shows the same face to Earth. On the day side of these planets, temperatures can reach over 2,500 degrees Celsius, hotter than some stars. The heat is so intense that molecules are ripped apart, clouds cannot form, and atoms like iron and titanium can exist as vapor, floating through the searing skies. In this extreme environment, the normal behavior of the atmosphere breaks down. Instead of getting cooler as you go higher, the upper layers of the atmosphere absorb the most radiation from the star and become hotter than the layers below. This is a thermal inversion, and it creates a totally different structure for the atmosphere compared to what we are used to seeing. When a planet passes behind its star, astronomers can subtract the light of the star alone from the combined light of the star and planet, revealing the planet's own glow. By looking at how this glow changes with different wavelengths of light, scientists can build a rough picture of how heat is distributed in the atmosphere. For planets like WASP 121b, one of the best-studied ultra-hot Jupiters, these observations showed something strange. Instead of light from deeper, cooler layers being seen, the spectrum showed the fingerprints of much hotter gas high up in the atmosphere. Molecules like water vapor, which should usually absorb heat at certain wavelengths, were instead glowing. A sure sign that the upper atmosphere was hotter than the lower layers. The cause of these thermal inversions seems to lie in the strange chemistry of ultra-hot Jupiter skies. At the enormous temperatures found on the day sides of these worlds, metals like titanium and vanadium can exist as gases. Compounds like titanium oxide and vanadium oxide are very good at absorbing ultraviolet and visible light from the star. When these compounds are present high in the atmosphere, they trap the star's energy before it can reach deeper layers, heating the upper atmosphere and creating the inversion. Some planets with similar temperatures seem to lack the chemical ingredients needed to trap heat in their upper atmospheres. In some cases, titanium and vanadium may have condensed into clouds and rained out, removing the materials that would otherwise create an inversion. In other cases, strong winds or magnetic fields might stir the atmosphere in ways that change how heat moves around. On Earth, weather patterns are shaped by the way heat moves up from the ground into the air. On an ultra-hot Jupiter with a thermal inversion, the prevailing conditions could drive some wild and unfamiliar weather systems. Winds may howl across the planet at thousands of kilometers per hour. Giant standing waves, driven by the constant glare of the star, could circle the planet's equator. Night-side temperatures, while cooler than the day-side, can still be hotter than anything found on Earth. At the temperatures found on the day-sides, gases become ionized, meaning that atoms lose electrons and turn into charged particles. These charged gases interact strongly with magnetic fields, possibly slowing down winds and changing the way heat is carried around the planet. Some models suggest that magnetic effects could create hotspots that shift away from the point directly under the star, leading to complicated patterns of day and night temperatures. Observations from space telescopes like Hubble, Spitzer, and JWST have opened a window into these bizarre worlds. JWST's infrared eyes in particular can measure the heat coming from ultra-hot Jupiters in exquisite detail, allowing astronomers to probe different layers of the atmosphere and map out temperature structures more precisely than ever before. What they are finding is that no two ultra-hot Jupiters are exactly alike. Some have strong thermal inversions, while others have none. Some show signs of complex chemistry, while others appear simpler. This diversity suggests that even among the hottest and most extreme planets, there are many paths that atmospheric evolution can take. Studying these planets helps scientists sharpen the tools they will need to study smaller, cooler planets in the future, including Earth-like planets that might one day show signs of life. Techniques for analyzing planetary atmospheres, separating out the faint light of a planet from the overwhelming glare of its star, and interpreting the complex signals in that light are being tested and improved by looking at these fiery giants first. Thermal inversions also hint at the wide variety of climate possibilities across the galaxy. On Earth, the presence of a temperature inversion in the atmosphere, such as when a layer of warm air traps cooler air below it, can lead to pollution buildup, fog, and strange weather patterns. On an ultra-hot Jupiter, the effects could be even more dramatic. The physics and chemistry we know from Earth can be pushed to their limits, and sometimes beyond, when faced with the intense conditions found elsewhere in the universe. Retrograde orbits, exoplanets defying angular momentum. When a star forms from a swirling cloud of gas and dust, that cloud spins in a certain direction. The planets that form from the leftover material inherit this same spin, orbiting the star in the same direction it rotates. It is a natural outcome of how stars and planets are born, and for a long time astronomers thought it was the rule everywhere. But as we started to look at various exoplanets, we found that some planets were moving the wrong way. These are planets with retrograde orbits. Instead of traveling around their stars in the same direction the star spins, they orbit in the opposite direction. To imagine this, think of a merry-go-round spinning one way, but a horse on the edge moving backward against the flow. In a cosmic sense, retrograde orbits are rare and unexpected. Their existence hints at stories of worlds that did not form gently, but were tossed and thrown by powerful forces. Early methods for finding exoplanets, like the radial velocity technique, could not easily tell the direction of a planet's orbit. More detailed measurements, especially using a method called the Rossiter-McLaughlin effect during transits, revealed the truth. As a planet passes in front of its star, it blocks part of the spinning surface. If the planet moves with the star's spin, it first blocks the side spinning toward us, then the side spinning away. But if the planet moves against the spin, the pattern is reversed. Careful studies of these tiny signals showed that some planets, instead of moving with their star's rotation, were fighting against it. One of the first and most famous retrograde planets found was WASP 17b, a giant gas planet twice the size of Jupiter, but with half the mass. It orbits its star in the wrong direction, and does so at a close distance, completing an orbit in just a few days. Since then, many more retrograde planets have been found, and they are often hot Jupiters. Normally, in a quiet young planetary system, the material in the disk around a star spins the same way, and planets grow in stable, circular orbits. For a planet to end up moving backward, it must have been knocked or pushed somehow after its birth. There are several ways this could happen. One idea is that close encounters with other planets could cause wild changes. If two giant planets form close together, they might start to tug on each other's orbits over millions of years. One planet could be thrown inward toward the star, while the other is ejected entirely from the system. In this violent exchange, a planet's orbit could be tilted or even flipped, ending up retrograde. Another idea involves the influence of a distant companion, like another star or a massive planet far away. Over time, the gravitational pull from this companion could slowly tilt the orbit of a planet, using a process called the Kozai mechanism. This effect can drive a planet into a highly tilted or retrograde orbit, especially if the companion's orbit is itself tilted relative to the original plane of the system. Yet another possibility is that the planet migrated inward through the disk of gas that surrounded the young star. If that migration happened in a chaotic way, such as through interactions with clumps of material or other young planets, the planet's orbit could be flipped. Retrograde planets are not born backward. They are shaped that way by a long chain of events, each leaving its mark on the system. When we find a retrograde planet, it is like finding a scar, evidence of a past conflict that shaped the present. Finding and studying these backward-moving planets helps scientists piece together how planetary systems evolve. Our own solar system is very orderly by comparison. The planets orbit in nearly the same plane and move in the same direction as the Sun spins. This order suggests a relatively quiet history. The question of why hot Jupiters are so often found in retrograde orbits is still open. One idea is that the process of moving inward to a tight orbit itself is messy. Gas giants are thought to form far from their stars, where it is cool enough for gas to condense. To reach a close orbit, they must migrate inward. If that migration happens through slow, smooth interactions with the disk, the planet should stay aligned with the star. But if the migration happens through gravitational chaos, through planet-on-planet battles or Kozai-driven flips, the final orbit can end up highly tilted or even backward. New observations continue to show the diversity of orbital alignments. Some planets are well aligned, orbiting neatly with their star's spin. Others are tilted at strange angles. Some even have polar orbits moving over the poles of their star rather than around the equator. And a few have true retrograde paths. Hotter stars, those larger and more massive than the Sun, seem to host more misaligned and retrograde planets. One reason might be that hotter stars have thinner outer layers, which makes it harder for tides between the star and planet to pull the orbit back into alignment. Over billions of years, tidal forces can realign a planet's orbit with the star's spin, but if the star's structure makes this process weak or slow, the planet can stay tilted for much longer. In some cases, the same tidal forces that slowly pull on a planet's orbit can also cause the planet to spiral inward, falling into the star over millions or billions of years. A retrograde planet may be especially vulnerable to this slow death because its backward motion creates stronger tidal stresses. Over cosmic timescales, many hot Jupiters may end their lives by being swallowed by their stars. Circumbinary planets on perilous paths. Stability in twin star systems. Circumbinary planets are worlds that do not orbit just one star, but instead move around a pair of stars locked together by gravity. What once seemed like an impossible place for a stable planet is now known to be surprisingly common, although the paths these planets follow are often delicate and full of hidden dangers. The discovery of circumbinary planets showed astronomers that nature could build stable systems, even in environments that seem chaotic at first glance. In a twin star system, the gravitational forces are constantly shifting. As the two stars orbit each other, they create a complex pattern of pull and tug that can easily disrupt a small planet's orbit. Yet somehow, in certain conditions, planets find ways to survive and thrive. One of the first confirmed circumbinary planets was Kepler 16b, often called the Tatooine planet, because of its two suns. Kepler 16b is a gas giant about the size of Saturn. It orbits around its two parent stars in a wide, stable path. When astronomers found it, They realized that it must have formed from the same disk of material that surrounded the two young stars, a disk that was itself shaped by the stars' dance. If a planet orbits too close to the two stars, their combined gravity will pull it apart or toss it out into space. If it orbits far enough away, the star's individual pulls blur into a single, more predictable force, and the planet can settle into a stable orbit. There is a critical distance, often about 2 to 4 times the separation between the two stars, where stable orbits become possible. This balancing act creates what astronomers call a stability zone. Inside this zone, a planet can move safely around both stars, feeling their combined gravity as if they were one. Outside the zone, chaos reigns, and any planet that ventures too close is likely to be lost. Even within the stability zone, the path of a circumbinary planet is not perfectly smooth. As the stars move around each other, they create small changes in the planet's orbit, making it wobble or shift over time. These wobbles are not enough to throw the planet out, but they do make its motion more complicated than a simple circle or ellipse. Some planets even show signs of their orbits slowly changing over long periods. In a single star system like our own, the planet-forming disk is usually thin and flat, with material moving in neat circles. In a binary system, the disk is often warped or twisted by the gravity of the two stars. Gaps can open up in the disk, and material can be pushed outward or inward in strange patterns. Despite these challenges, planets can still form from the leftover dust and gas, growing slowly as they collect material from the disk. It is not entirely clear how these planets managed to grow large enough to survive the early chaos. Some models suggest that planet formation starts farther out, in quieter parts of the disk, and then the planets slowly move inward to their current positions. Others propose that planets form right at the edge of the unstable zone, where material can pile up and create dense clumps. Circumbinary planets may be rare compared to planets around single stars, but among the systems that do exist, the planets we have found show a surprising range of sizes and types. Some are gas giants like Kepler 16b, while others are smaller, rocky worlds more similar to Earth. The discovery of rocky circumbinary planets is especially exciting because it raises the possibility of habitable worlds orbiting two suns. Finding these planets is not easy. In binary systems, the stars are moving too, which means that the timing of a planet's transit changes from one orbit to the next. Astronomers must carefully study the light from the system, watching for these irregular patterns to reveal the hidden planet. In some cases, the planet can cause tiny changes in the timing of the star's own orbits, providing another clue to its presence. Despite these challenges, telescopes like Kepler have uncovered a growing list of circumbinary planets. Living on a circumbinary planet would present its own set of challenges. The two suns would create complex patterns of day and night, with light levels rising and falling as the stars move in the sky. Seasons would be shaped not just by the tilt of the planet's axis, but also by the changing positions of the stars. Some parts of the planet might experience long periods of daylight, followed by extended nights, depending on the details of the orbits. The habitable zone can be narrow in a binary system and can shift over time as the stars move. A planet in the right spot could experience enough stability to support life, but it would have to endure the gravitational and light variations that come with orbiting two suns. Recent studies suggest that circumbinary planets can maintain stable climates under the right conditions. If the planet's orbit is nearly circular and the stars are not too wildly different in size or brightness, the changes in sunlight can be modest enough for life to adapt. On the other hand, if the stars are very different, or the orbit is highly elongated, the planet could swing between extreme heat and cold, making life much harder. Some scientists believe that binary systems might even offer advantages for life. Two stars could provide a more stable energy supply over billions of years, reducing the risk that one star's changes would wipe out a growing biosphere. In other cases, the presence of two suns could create complex chemical environments that help kickstart the development of life. Thornzitco objects, stars within stars merged with neutron cores. A Thornzitco object, or TZO, is a theorized concept of a star within a star, a rare and wild merger where a neutron star becomes trapped inside a giant burning sun. The idea of the Thornzitco object was first proposed in the 1970s by Kip Thorne and Anna Zitkow, two astrophysicists who were exploring what happens in certain exotic stellar collision scenarios. Imagine a neutron star drifting close to a red supergiant. Their gravitational fields pull on each other until finally the neutron star plunges into the giant's enormous outer layers. Instead of simply passing through or being torn apart, the neutron star sinks deeper into the heart of the red giant, eventually coming to rest in the center. What forms is something never seen in our own solar system, or even confirmed in the wider galaxy? A TZO. At first glance, a TZO might look like any other red supergiant. It would be huge, glowing with a reddish hue, and shedding mass through a slow, windy outflow. But deep inside, hidden under layers of gas and plasma, the heart of the star would be very different. Instead of a normal fusion-burning core, there would be a neutron star, an object so dense that a teaspoon of its material would weigh billions of tons. Normally, a star's core produces energy through nuclear fusion, turning hydrogen into helium, and later on, heavier elements. In a TZO, fusion would still happen, but in ways never seen in normal stars. The neutron star's surface, surrounded by an ocean of stellar material, would become a site for exotic nuclear reactions. These reactions could produce rare elements, like lithium and molybdenum, in quantities much greater than what is found in other stars. These nuclear processes, called the rapid proton capture process, involve protons slamming into atomic nuclei at incredible speeds. The results are new kinds of matter, strange isotopes that are not usually made inside stars. If scientists could study a TZO up close, they might see these odd chemical fingerprints in its light. But TZO are still only a theory. Finding one has proven incredibly difficult. They are thought to be very rare, the result of unlikely cosmic accidents. Even when they do form, they would blend in among the thousands of normal red supergiants scattered across galaxies. Only by carefully analyzing the chemical makeup of a giant star, looking for those unusual elements, could astronomers possibly spot one. In recent years, there have been a few candidates. In 2018, scientists studying a red supergiant named HV 11417 in the Tucana constellation found signs that it might be a TZO. If it is confirmed, it would be the first known TZO, a living proof of this rare cosmic phenomenon. However, confirmation is not easy. Stellar atmospheres are complex, and some of the chemical signs that might point to a TZO could also be explained by other processes, like unusual internal mixing in massive stars. Astronomers need better models, more detailed observations, and probably a little bit of luck to know for sure. The formation of a TZO would be a violent and chaotic event. When the neutron star plunges into the giant, friction between the neutron star and the surrounding gas would release enormous amounts of energy. The outer layers of the red giant could be disturbed or even partly blown away. Over time, the neutron star would spiral toward the center, sinking deeper and deeper as drag slows it down. The result would be a strange temporary balance. A neutron star resting in the dense core of a bloated, dying star. But this balance would not last forever. As the TZO evolves, it might lose mass through stellar winds. As it sheds its outer layers, the object could eventually collapse into a black hole, or the neutron star might merge with the stellar core completely, creating new types of explosions or gravitational wave signals that we have not yet observed. TZOs are strange intersections, the result of chance encounters in crowded star clusters or dense stellar nurseries. Even as we map the movements of galaxies and study the atmospheres of exoplanets, there are rare and strange objects hidden in plain sight. They might look ordinary from far away, but inside they carry stories of violence, survival, and transformation. Tightly packed resonant chains. Located about 40 light-years away, Trappist I is a small, cool red dwarf star surrounded by at least 7 Earth-sized planets. What makes this system remarkable is not just the number of planets, but how closely they are spaced and how their orbits are linked. Each planet's orbit is connected to its neighbors through gravitational resonance, creating a chain that holds the entire system together. In Trappist I, for example, every time the innermost planet orbits the star 8 times, the next planet out orbits 5 times. This 8:5 ratio is a type of resonance. Similar resonances exist between other neighboring planets in the system. These ratios mean that the planets are constantly tugging on each other with just the right amount of force to keep their orbits stable. Resonance acts like a protective shield against chaos. Without it, the planets would pull on each other in unpredictable ways, slowly shifting their orbits until collisions or ejections became inevitable. But with resonance, each tug is timed perfectly. The planets speed up or slow down just slightly at the right moments to keep everything in balance. It is a situation that can only happen under very specific conditions. Most likely, these systems form in a much looser way, with planets scattered across different orbits. Over time, interactions with the remaining gas and dust in the system cause the planets to migrate. As they move, they can become trapped in resonances with each other. Once trapped, they stay locked unless something major disturbs them. These tightly packed systems are living right at the edge of what is possible. In many cases, if the orbits were just a little bit different, if one planet moved slightly faster or slower, or if their distances were slightly changed, the system could become unstable. A small difference could build up over millions of years, eventually causing the planets to cross paths and collide, or to be flung out into deep space. Scientists believe that the process of forming a resonant chain requires a lot of fine-tuning. The planets must migrate through the disk of gas and dust at just the right speed, and they must encounter each other at the right times. If they migrate too quickly, they can pass through resonances without becoming trapped. If they move too slowly, they might collide before resonance can stabilize them. It is a race against time and gravity. Even after a resonant chain forms, it remains vulnerable. A passing star could nudge the system with its gravity, breaking the delicate timing. Or, after the gas and dust are gone, other effects like radiation pressure or even the gentle tugs from each planet's own tides could slowly change the orbits. Over billions of years, a system that once seemed perfectly balanced could fall apart. Not all resonant chains are as tight as Trappist I. Some systems have fewer planets or weaker resonances, but in general, when astronomers find multiple planets very close together around a star, they often find hints of resonance linking them. It seems to be nature's way of allowing many planets to share the same small region of space without destroying each other. Interestingly, our own solar system shows signs of past resonance. Jupiter's moons, Io, Europa, and Ganymede, are locked in a famous one. 2-4 resonance. For every orbit Ganymede makes, Europa completes 2 and Io completes 4. This resonance helps maintain the moon's orbital shapes and drives tidal heating that makes Io volcanically active and keeps Europa's subsurface ocean from freezing. But among the planets themselves, there are no tight resonant chains like those seen in Trappist I. Some think that the solar system may have once had tighter resonances, but they were broken during a period of instability long ago, when the giant planets migrated and disturbed the system. This hints that resonant chains are delicate and may not survive forever. In a system like Trappist I, where several planets orbit in or near the habitable zone, resonance can help stabilize climates over long periods. Without resonance, small changes in one planet's orbit could ripple through the system, causing wild swings in temperature and radiation levels. With resonance, the system can maintain more predictable conditions, giving life a better chance to emerge and survive. On the other hand, the close spacing of the planets could lead to strong tidal forces that create extreme volcanism or other harsh conditions. In some cases, the gravitational tugs between planets could even cause slow shifts in their orbits that eventually push them out of the habitable zone. So while resonance can promote stability, it can also carry hidden risks. These resonant chains reveal a side of the universe where order and chaos are always just a heartbeat apart. Some resonant chains may remain stable for billions of years, while others may already be ticking time bombs, set to unravel in the distant future. Rogue planets adrift, starless wanderers in interstellar space, somewhere between the stars, far away from any familiar solar system. There are planets that drift alone in the darkness. These are rogue planets, wanderers moving through the galaxy without a parent star to light their skies. These planets are truly free-floating, slipping through interstellar space like ships without a harbor. They follow paths shaped only by the pull of the galaxy itself. It is a silent, cold journey that can last billions of years. Finding these rogue planets is a major challenge. Planets are small and do not give off light like stars do. When a planet is not lit up by a nearby sun, it becomes almost invisible against the blackness of space. Most of the time, astronomers can only detect rogue planets through indirect methods. One of the best tools for this is gravitational microlensing. This happens when a rogue planet passes exactly between us and a distant star. The gravity of the planet bends the star's light, briefly making it look brighter. It is a rare event, but when it happens, it can reveal the presence of a hidden planet. Some studies estimate there might be as many rogue planets in our galaxy as there are stars, maybe even more. It means that the Milky Way could be filled with hundreds of billions of these lost worlds, traveling silently through the cosmic void. Where do rogue planets come from? Scientists think there are two main possibilities. Some rogue planets might have formed in the same way that stars do, from clouds of gas and dust that collapse under their own gravity. If a cloud is too small to ignite fusion and become a star, it might instead form a planet-sized object. These would be true primordial rogue planets, born alone and never tied to any star. Other rogue planets likely started their lives in regular solar systems, orbiting stars just like Earth does. But something went wrong. In crowded young systems, if a planet gets too close to a larger neighbor, it can be flung out into space. Violent encounters with other stars passing nearby could also eject planets from their homes. In these cases, rogue planets are the victims of gravitational chaos, cast away to drift forever. Some of these ejected planets might even have started as gas giants like Jupiter. But without the warmth and radiation of a nearby star, their atmospheres could change dramatically over time. The thick gases could cool and settle, perhaps even freezing solid in the extreme cold of deep space. Life on a rogue planet, if it could even exist at all, would be very different. Without sunlight, there would be no photosynthesis to support life at the surface. But some scientists have speculated that if a rogue planet had a thick enough atmosphere, it could trap heat from its own core for billions of years. Volcanic activity could provide warmth and energy. Deep underground, oceans of liquid water could exist, kept from freezing by geothermal heat. Some rogue planets might have thick layers of hydrogen gas, which acts like a giant insulating blanket. Underneath this layer, temperatures could be warm enough for liquid water, even without a star. These stealth habitable worlds would be hiding their potential for life deep beneath their dark, frozen exteriors. Some rogue giant planets can be many times the mass of Jupiter. These behemoths might have moons orbiting them, much like Jupiter and Saturn do. In theory, these moons could also hold subsurface oceans, warmed by tidal forces if the moon's orbits are eccentric enough. A rogue planet entering a star system like ours would be a dramatic event. Its gravity could disrupt the orbits of planets and comets, possibly even leading to collisions or sending objects hurtling toward the inner planets. Thankfully, the vast emptiness of space makes such encounters incredibly unlikely. A rogue planet would have to pass very close to the Sun to cause serious trouble, and the chances of that happening are slim over the lifetime of the solar system. Still, the idea that there are so many orphan planets out there changes how we think about the galaxy. Stars are no longer the only landmarks. Between them, there are countless invisible worlds. Missions like the Roman Space Telescope, with its powerful microlensing capabilities, are expected to uncover many more of these hidden travelers. Infrared surveys, which can detect the faint heat from cold objects, might also reveal rogue planets that are still warm from their formation. Some astronomers dream of sending spacecraft to visit rogue planets someday, although it would be an incredible technical challenge, given the vast distances and the fact that rogue planets do not stay in one place. It is not impossible to imagine a probe setting out to chase down one of these dark worlds. R. Coronae borealis. Variables, giants that vanish in dust. R. Coronae. Borealis variables, or RCB, are a rare type of supergiant star. Most stars that change in brightness, called variable stars, do so because of pulsing changes in their interiors. They swell and shrink, heat up and cool down in steady rhythms. But the RCB stars tell a different story. Their changes are not so orderly. They can stay steady for months or years, then without any warning, their light dims dramatically, sometimes by factors of 1,000 or more. The first discovery of this strange type of star happened more than 200 years ago. Astronomers watching the star, R. Coronae borealis itself, noticed that it dimmed sharply for a period of time before returning to its usual brightness. Over time, more stars behaving in a similar way were found, although they remain very rare. Only a few dozen are known in the Milky Way. The key to understanding these stars lies in their unusual atmospheres. RCB stars are extremely rich in carbon. Unlike normal stars like the Sun, where hydrogen is the most abundant element, these supergiants have burned through much of their hydrogen. Instead, their outer layers are filled with helium, carbon, and heavier elements. This strange chemistry creates the perfect conditions for something very odd to happen. At random intervals, the atmosphere of an RCB star cools just enough in patches to allow carbon atoms to stick together. These carbon atoms form tiny soot-like particles, a kind of cosmic smoke. Once these particles form, they quickly multiply, creating thick clouds of black dust. This dust doesn't stay put. It spreads outward from the star, forming a dense veil that blocks the star's light from reaching Earth. To an observer, it looks like the star has suddenly vanished. These episodes of dimming can last for months or even years. Over time, radiation from the star pushes the dust cloud away, or the dust disperses naturally. When the cloud clears, the star's light brightens once again, returning it to its usual appearance. But there is no telling when the next dimming event might happen. It could be decades apart, or only a few years. The unpredictability of RCB stars makes them fascinating objects to study. Each one has its own pattern of fading and brightening, shaped by its mass, temperature, and the conditions in its atmosphere. Some stars have small, frequent dimmings, while others vanish almost completely for long stretches of time. Astronomers believe that the origin of these stars is as strange as their behavior. One theory is that RCB stars are the products of mergers, the collisions of two white dwarfs, the dense remnants left behind after stars like the Sun die. If two white dwarfs, one rich in helium and the other in carbon and oxygen, spiral together and merge, they might create a new massive star with the strange chemistry needed for these dust clouds to form. Another possible origin story involves the late stages of stellar evolution, when a single massive star sheds its outer layers and briefly becomes a hydrogen-poor, carbon-rich giant before fading into a white dwarf. The carbon dust that these stars create is not just a local phenomenon. Over time, as the stars lose mass through repeated ejections, they enrich the surrounding interstellar space with carbon grains. These grains could go on to become part of future generations of stars and planets. In a way, RCB stars may be important contributors to the chemical makeup of galaxies, helping to spread the building blocks of complex molecules and life. Modern telescopes allow astronomers to monitor these stars across many wavelengths, from visible light to infrared. In infrared light, where dust is more transparent, astronomers can still see the hidden star shining through the dust clouds. Infrared observations have also revealed details about the structure of the dust clouds themselves. They are not smooth and even, but clumpy, with holes and gaps. This explains why the dimming is often irregular. Sometimes the star flickers slightly before being completely hidden as the clouds thicken and move. Studying these dusty events has given astronomers a better understanding of how dust forms in space. It is one thing to know that stars produce dust. It is another to watch the process happen almost in real time. The carbon grains from the stars are similar to those found in meteorites on Earth, suggesting that dust from ancient stars like these helped seed the early solar system. Losing mass through constant dust production means that the star is gradually shrinking, shedding its outer layers bit by bit. Eventually, it will lose enough mass that it can no longer sustain itself as a supergiant. It will collapse inward, fading into a white dwarf and joining the many millions of faint stellar remnants scattered across the galaxy. Magnetars, engines of magnetic mayhem. Magnetars are a rare type of neutron star where the magnetic field is so strong it bends the very fabric of atoms and space around it. Even thousands of kilometers away, they would wipe information from a credit card or tear apart human biology without warning. Magnetars are born in the aftermath of a supernova, when a massive star exhausts its fuel and collapses under its own gravity. The core of the star, no larger than a city, is squeezed so tightly that protons and electrons are forced together into neutrons, forming a neutron star. Under normal conditions, a neutron star already has an extremely strong magnetic field, billions of times stronger than Earth's. But in rare cases, something different happens. Through processes scientists still do not fully understand, some newborn neutron stars end up with magnetic fields that are 1,000 times stronger than even the typical ones. These become magnetars. Some magnetars have fields reaching 1 billion Tesla, or about 1,000,000 billion times stronger than the magnetic field of Earth. At this strength, the magnetic forces are so powerful they actually change the properties of empty space itself. In quantum physics, empty space is not truly empty. It is a seething field of virtual particles popping in and out of existence. Under a magnetar's influence, even this vacuum behaves differently, affecting how light and radiation move. This extreme magnetic environment gives rise to some of the most violent outbursts observed in the universe. When a magnetar's magnetic field shifts or snaps, much like an earthquake relieving stress along a fault line, it releases an enormous amount of energy in the form of X-rays and gamma rays. These flares can be so intense that they briefly outshine everything else in the galaxy. In 2004, a magnetar known as SGR 1806-20 released a flare that was so powerful it affected Earth's upper atmosphere from a distance of about 50,000 light-years. The surface of a magnetar is a tortured place. Its crust, made of iron and other heavy elements, is held together under enormous pressures. But even here, the magnetic forces are stronger than the forces holding atoms together. The crust can crack and shift as the magnetic field strains against it, leading to sudden flares. These starquakes release not only radiation, but also powerful magnetic waves that ripple outward into space. Even though magnetars are incredibly violent, they are also short-lived in cosmic terms. Their magnetic fields decay relatively quickly, over a period of about 10,000 to 100,000 years. As the field weakens, the magnetar becomes quieter and fades into a more typical neutron star. For astronomers, catching a magnetar in its active phase is a rare opportunity to study one of nature's most extreme phenomena at work. Most known magnetars are discovered because of their bursts of high-energy radiation. Satellites like NASA's Swift and Fermi spacecraft monitor the sky for sudden X-ray or gamma-ray outbursts, and many magnetars have been found this way. Sometimes, however, magnetars reveal themselves in more subtle ways, such as through their steady but unusually strong X-ray emissions, even when not flaring. The environment around a magnetar is just as strange as the star itself. The magnetic field can trap and twist plasma into strange structures. It can also slow down the star's rotation very quickly. While certain neutron stars called pulsars spin rapidly, sometimes many times per second, magnetars tend to rotate more slowly. A magnetar may complete one rotation every few seconds to tens of seconds, a result of the drag caused by its immense magnetic forces. Magnetars may play key roles in some of the biggest questions in astronomy. Some scientists believe that magnetars could be linked to fast radio bursts, or FRBs, brief, powerful radio signals from distant galaxies that last only milliseconds. The exact cause of FRBs is still unknown, but in a few cases, magnetar flares have been observed at the same time as FRBs, suggesting a connection. Another potential link involves the mystery of how heavy elements like gold and platinum are formed in the universe. It has been suggested that when two neutron stars merge, or when a magnetar collapses into a black hole, conditions could be right to forge these heavy elements. If so, magnetars might have helped seed the early universe with some of its most precious materials. Why do some neutron stars become magnetars while others do not? How exactly do their magnetic fields become so strong in the first place? Scientists are still piecing together the answers. Some theories suggest that rapid rotation during the collapse of the original star can amplify magnetic fields through a dynamo effect, similar to how Earth's magnetic field is generated, but on a much more powerful scale. Other theories propose that special conditions during the supernova itself may be required. They are rare. Only about 30 are known in our galaxy. Their bursts are unpredictable, and most of the time they are quiet. But when they do flare, they send messages across the cosmos of unimaginable pressures, forces, and energies. On Earth, the strongest magnetic fields created in laboratories are about 100 Tesla. These are considered extreme and require huge equipment and safety precautions. Magnetars exceed this by factors of millions or billions. If a magnetar were placed within 1,000 kilometers of Earth, it would destroy the planet's magnetic field, atmosphere, and surface in seconds, stripping electrons from atoms and leaving the planet a lifeless rock. Fortunately, magnetars are far away. Their power remains something we can observe only from a safe distance, a reminder of the violent and unpredictable forces that still shape the universe today. In the silent, cold reaches of space, these hidden engines of magnetic fury continue to spin, crack, and flare, creating bursts of energy that race across the galaxy at the speed of light, brief but unforgettable signs of the unimaginable powers locked inside these small, densest stars. Pulsar planets, worlds orbiting stellar corpses. Pulsars are neutron stars that emit beams of radio waves from their magnetic poles. As they spin, these beams sweep across space like cosmic lighthouses, creating a steady pulsing signal that can be detected from Earth. It was while studying one of these strange remnants that astronomers made an unexpected discovery: planets. In 1992, two astronomers, Alexander Volskshan and Dale Frail, were observing a pulsar known as PSRB 1257+12, later given the name Lich. Lich was located about 2,300 light-years from Earth. They noticed that the timing of the pulses was slightly irregular. Instead of arriving with perfect regularity, the pulses showed tiny variations, as if something was tugging on the pulsar's motion. After careful analysis, they realized these variations could be explained by the presence of planets orbiting the pulsar. Planets, it seemed, could exist even around dead stars. The planets around Lich were the first confirmed exoplanets ever found, and it was a completely different picture of what a planetary system could look like. Neutron stars emit powerful radiation across many parts of the electromagnetic spectrum, including X-rays and gamma rays. For a planet to survive so close to a pulsar is incredible. Any atmosphere would likely be stripped away quickly unless it was somehow replenished or shielded. Yet these planets do exist, and they orbit very close to the pulsar. In the case of Lich, the two main planets are about 4 and 3 times the mass of Earth, and they orbit at distances smaller than that of Mercury around the Sun. Pulsar planets are thought to form in a few different ways. One idea is that they are survivors, planets that somehow lived through the supernova explosion of their parent star. However, most planets would likely be destroyed or flung away during such a violent event. Another possibility is that the planets formed after the supernova, from the debris left behind. A disk of gas and dust could have circled the pulsar, providing the raw material for new planets to assemble. In this way, pulsar planets could be considered second-generation worlds, born not from the calm coalescence of a stellar nursery, but from the wreckage of a stellar death. They orbit a dead, cold core surrounded by intense radiation fields. They experience gravity so strong that even a small change in their orbits would have dramatic effects, yet they remain in stable orbits, spinning quietly around a beacon of death. Despite many searches, only a handful have been confirmed. This rarity might be partly because pulsar planets are difficult to detect. The pulsar's radio beams are easy to measure for timing changes, but planets must be relatively massive and close to cause noticeable effects. Also, many pulsars are in binary systems with other stars, complicating the search for small wobbles. Still, the scarcity also likely reflects harsh formation conditions. Not every neutron star gets to build a new planetary system after its violent beginning. Another famous pulsar with planets is PSRB 1600-2026, located in a globular cluster called M4, about 12,400 light-years away. Here, a planet about 2.5 times the mass of Jupiter orbits a neutron star and a white dwarf in a wide orbit, forming a strange three-body system. This planet is often called a Genesis planet because it is thought to be extraordinarily old. At 12.7 billion years, it formed less than a billion years after the Big Bang. This system is even more complex because it is located inside a dense stellar environment where stars are packed tightly together. Such an environment would usually make planetary systems unstable. The fact that this planet still exists suggests it either formed there under rare conditions or somehow migrated there after formation. The skies of pulsar planets would not be filled with warm light, but instead dominated by harsh radiation. The gravitational pull would be relentless. Any atmosphere, if it existed at all, would have to be continually renewed by volcanic activity or protected by strong magnetic fields. Even so, it's hard to imagine these worlds as hospitable. People have speculated what it would take for life to exist on pulsar planets. The high-energy radiation would be a major obstacle. But if a planet had a very thick atmosphere or oceans deep enough to shield life from radiation, it is not entirely impossible that simple life forms could survive. Others suggest that life could exist underground, protected from the constant particle bombardment at the surface. Studying pulsar planets also offers practical benefits. The precise timing of pulsars makes them like cosmic clocks. Small changes caused by planets can be detected with incredible sensitivity. This method of detection, pulsar timing, is so accurate that it has been proposed as a way to navigate spacecraft across the solar system and even beyond. Using pulsars like lighthouses in deep space could one day help humans travel across the stars. Helium-rich blue large amplitude pulsators. Most variable stars, stars that change their brightness over time, owe their pulsations to hydrogen. Hydrogen is the most common element in the universe and acts as the fuel for the majority of stars. Inside many variable stars, hydrogen plays a major role in creating pressure and movement in the star's layers. As the star burns, it expands and contracts in a rhythmic way, causing its brightness to rise and fall. This is the case with well-known classes of variable stars like Cepheids and RR Lyrae. But helium-rich blue, large-amplitude pulsators, or BLAPs, tell a different story. Instead of hydrogen, their changes are driven by helium. Their outer layers are mostly helium, not hydrogen, and it is helium that controls how they pulse. This makes them fundamentally different from most other pulsating stars known today. The first signs of these unusual stars were found only recently in the past decade. Astronomers using large sky surveys noticed stars that did not match any known categories. These stars showed rapid, large changes in brightness, some brightening and dimming by as much as 30% in just a few hours. Their colors showed they were very hot, giving them a blue appearance, and their light patterns suggested something unusual was happening inside them. Detailed studies revealed that these stars had very thin hydrogen layers, or none at all. Instead, helium dominated their outer envelopes. This was a surprise because in most stages of stellar life, hydrogen is still the most visible part of a star. For a star to be mostly helium on the outside, something extreme must have happened to strip away its hydrogen. Perhaps they were once part of a binary star system, where two stars orbit closely together. In such systems, one star can steal material from the other. If one star pulls off most of its neighbor's hydrogen envelope, it can leave behind a helium-rich remnant. Another idea is that these stars might be the results of stellar mergers. If two white dwarfs merged, they could create a new, hot, helium-rich star. No matter how they formed, the important feature is the same. Helium is now the main actor. The pulsations in these stars come from a process known as the Kappa mechanism, the same basic engine behind many variable stars. But here, it is helium atoms that take on the job rather than hydrogen. As the helium layers heat up, they trap energy, causing the star to expand. Then, as they cool, they release that energy and the star contracts. This cycle of expansion and contraction produces the powerful brightness changes we see from Earth. The discovery of these blaps opens a new window into the late stages of stellar evolution. These stars are rare, and their lifetimes are probably short in cosmic terms, which may explain why they are so hard to find. Their discovery suggests there may be many more short-lived exotic objects in the galaxy that have gone unnoticed simply because they are rare or because their periods of activity are brief. If many of them were formed through binary interactions, it highlights how common and important binary evolution might be across the universe. It also offers new insights into how stars shed their outer layers, and how white dwarfs might sometimes get a second chance at life, however short. Many variable stars pulsate over the course of days or weeks, but blaps can complete a full cycle of brightening and dimming in just a few hours. This rapid heartbeat gives them a sense of urgency and drama not seen in slower variables. It also makes them easier to study over a short observing period, since astronomers can watch a full pulsation happen in a single night. The temperatures of these stars are very high, around 30,000 degrees Celsius. This intense heat gives them their blue color. It also suggests that they are burning through their remaining fuel quickly, racing toward an inevitable collapse into a white dwarf or even a more exotic state, depending on their mass. Helium is more opaque at certain temperatures, which helps trap heat and create the instability that drives the pulsations. This means that, while the basic mechanism behind the pulsations is similar to other variable stars, the details are different. Small changes in the properties of the helium envelope can have large effects on the brightness and timing of the pulses. By studying their pulsations carefully, astronomers can learn about the internal structure of the star. Just as earthquakes help scientists study the interior of Earth, the pulsations of a star can reveal its inner layers. This field, known as astroseismology, allows scientists to probe the otherwise invisible interiors of distant stars. In the case of blaps, astroseismology may offer some of the best ways to test models of how these rare stars formed and evolved. Because helium behaves differently from hydrogen under pressure and temperature changes, the seismic waves moving through these stars can tell astronomers unique things. It offers a rare laboratory to test our theories of how matter behaves under extreme conditions beyond what we can replicate on Earth. Are there stars dominated by other elements, like carbon or oxygen? Could even stranger stars exist, with combinations of materials we have not yet observed? Each new discovery, like helium-rich blaps, reminds scientists that the universe is far more creative than we imagine in the ways that it uses matter, energy and time to weave beauty across the cosmos. Hypervelocity stars, galactic slingshots, exceeding escape velocity. Hypervelocity stars are different from normal runaway stars, which are often thrown out of their home systems by supernova explosions. In those cases, when a massive star reaches the end of its life and explodes, it can throw nearby stars outward with enough force to leave their original neighborhood. Hypervelocity stars, however, have speeds so high that supernovas alone cannot explain them. Instead, these stars owe their launch to one of the most extreme objects in the galaxy, the supermassive black hole at the galactic center. The idea of stars being thrown out of the galaxy was first proposed in the late 1980s, but real evidence came later. In 2005, a young hot star traveling at a speed of over 2 million kilometers per hour was discovered speeding away from the center of the Milky Way. Its trajectory pointed directly back towards Sagittarius A star, the black hole hidden deep within a thick cloud of gas and dust at the galaxy's core. This star was moving fast enough that it would eventually leave the Milky Way entirely, drifting into intergalactic space. Near the center of the galaxy, stars often move in pairs, orbiting each other closely in binary systems. If a binary system ventures too near the black hole, the intense gravity can rip it apart. One star can be captured into a tight orbit around the black hole, while the other is flung outward at incredible speeds. This gravitational slingshot effect can launch the surviving star fast enough to escape not just the black hole's grasp, but the gravitational pull of the entire Milky Way. This process explains why many hypervelocity stars seem relatively young and massive. These are stars that once lived in the dense, chaotic environment near the galactic center, a place where interactions with the central black hole are possible. Their short lifespans mean they can be traced back to their place of origin before they burn out. Older stars, or stars with slower life cycles, might still be traveling, but by the time they are noticed, their early history may be harder to track. As more hypervelocity stars have been found, astronomers have used their movements to better understand the shape and mass of the Milky Way. Since the stars move through the galaxy's gravitational field, their paths can reveal how mass is spread out, including the hidden mass of dark matter. By tracing their orbits backward, scientists can also confirm that many of them did indeed start their journey near Sagittarius A star. Not all hypervelocity stars are thought to be launched by the supermassive black hole alone. Some may have been involved in complex gravitational interactions with clusters of other stars, or with intermediate mass black holes that could exist outside the galactic center. These other scenarios are still being studied, but the cleanest, fastest ejections seem to come from close encounters with the Milky Way's main black hole. For every million stars, perhaps only a handful are racing outward at these speeds. Finding them requires careful surveys of the sky, searching for stars that are not only moving quickly, but moving in the right direction, away from the galactic center. Not all of them are speeding directly outward in straight lines. Some have complex, arcing paths that reflect the uneven distribution of mass within the galaxy. Others may have been slowed slightly by interactions with clouds of gas, stars, or dark matter, though not enough to prevent their ultimate escape. Tracking these paths gives astronomers a better sense of the unseen structures that influence stellar movements. As they drift into the cold, empty spaces between galaxies, they will become isolated wanderers, living out the rest of their lives without the familiar backdrop of a galactic home. Some may eventually slow down if they encounter enough intergalactic material, but most will continue moving forever, lighting up small patches of deep space with their lonely glow. How often do stars venture close enough to the center to be thrown out? Are there periods of increased activity when the black hole's surroundings are more crowded and violent? Could some hypervelocity stars come from collisions between galaxies, where gravitational forces become even more chaotic? Hypervelocity stars are living witnesses to some of the most powerful forces in the universe. Their very existence proves that the black hole at the center of our galaxy is an active player in shaping the Milky Way's structure. By flinging stars outward, it leaves fingerprints on the galaxy's mass, shape, and future. Some hypervelocity stars carry clues about the environments close to black holes, places too dangerous for most matter to survive, yet crucial to the story of how galaxies grow and change over billions of years. Betelgeuse's Great Dimming, red supergiant's mysterious fade. In late 2019, astronomers around the world began to notice that Betelgeuse, the bright red shoulder of the constellation Orion, was fading. At first it was a subtle change, something that only careful observers with sensitive instruments might have caught. But over the weeks that followed, the dimming became obvious even to the naked eye. By early 2020, Betelgeuse had dropped to about a third of its usual brightness, its familiar brilliance reduced to a pale shadow of itself. This sudden and unexpected change sparked intense interest and concern. Betelgeuse is no ordinary star. It is a red supergiant, one of the largest and most luminous stars visible from Earth. It is nearing the end of its life, fusing heavier and heavier elements in its core as it prepares for the final act of its stellar existence, a supernova explosion. The idea that the dimming might signal an imminent supernova captured the public imagination. For a time, the world watched Orion's shoulder closely, wondering if they were about to witness one of the most dramatic events in the night sky. But nature, as it often does, turned out to be more complicated. As astronomers studied the dimming in more detail, they realized that it probably was not a direct prelude to a supernova. Instead, it pointed toward unexpected processes happening in the outer layers of the star. Two main explanations emerged. One was that Betelgeuse had undergone an episode of intense convection. In massive stars, energy from the core is carried outward partly through convection, huge bubbles of hot gas rising and cooler material sinking. These convective cells on Betelgeuse's surface are truly vast, much larger than the Earth itself. If one of these cells brought a cooler patch to the star's surface, it could cause the star's brightness to drop noticeably from our point of view. This would mean that the dimming was essentially a kind of giant sunspot, but on a far more massive and dramatic scale. The second explanation was that Betelgeuse had ejected a cloud of material that then condensed into dust. Massive stars like Betelgeuse are known to shed material into space as they age, creating complex and sometimes beautiful patterns of gas and dust around them. If a large amount of this material was expelled and then cooled quickly into tiny dust grains, it could have partially blocked the light from the star, causing it to appear dimmer from Earth. In this view, the Great Dimming was not a change in the star's energy output, but a case of cosmic clouds briefly veiling its light. Evidence collected in the months after the dimming suggested that the dust hypothesis was the more likely cause. Observations from instruments capable of seeing infrared light showed that Betelgeuse was not as dim in the infrared. This pointed towards something blocking visible light, rather than a true drop in the star's luminosity. Later images from the Hubble Space Telescope showed signs of material moving away from the star consistent with a major mass ejection. The Great Dimming highlighted how little we still understand about the late stages of massive star evolution. Betelgeuse is about 700 times the diameter of the Sun. If placed at the center of our solar system, it would engulf the orbits of Mercury, Venus, Earth, and possibly Mars. Its outer layers are so diffuse and tenuous that they are more like a dense wind than a solid surface. Understanding how such a structure behaves is difficult, especially when the internal processes driving mass loss are chaotic and hard to predict. One possibility is that Betelgeuse is entering a particularly unstable phase of its life, where its outer layers are shedding mass more quickly and unevenly than before. Some models suggest that as a star nears core collapse, it might experience increased instability, with more violent outbursts of convection and mass ejection. If so, Betelgeuse's Great Dimming might be an early warning sign, not of an immediate supernova, but of a star that is beginning to break down in more obvious ways. Yet it is important to remember that even on cosmic timescales, soon is relative. Betelgeuse might still have tens of thousands or even hundreds of thousands of years left before it finally explodes. The Great Dimming was a rare glimpse into the living dynamics of a dying star, but it does not give us a precise countdown clock. The dimming episode also gave astronomers a rare opportunity to test their models. With so much attention focused on Betelgeuse, Observations from all over the world and in many different wavelengths poured in. Some researchers used this event to refine ideas about how dust forms around massive stars. Others looked at how light curves, the graphs showing how a star's brightness changes over time, could be used to understand large-scale surface activity on distant suns. In the months that followed the peak of the dimming, Betelgeuse gradually returned to its former brightness. By mid-2020, it was shining with almost its usual strength, though small changes continued to ripple across its surface. This recovery supported the idea that the event was not a permanent change, but rather a temporary phenomenon. Without long-term careful observation, events like this could easily be missed or misunderstood. Modern astronomy increasingly relies on networks of ground-based telescopes, space observatories, and even amateur astronomers to keep an eye on the dynamic sky. Even stars we think we know well can surprise us. Are similar dimming events happening in other stars that we have not been able to observe closely enough? As the number and capability of telescopes around the world increases, astronomers hope to answer these questions. Observing many stars at different stages of their evolution will help build a more complete picture of how massive stars live and die. Ultra-diffuse galaxies with dark matter heavy cores, ghostly giants. Ultra-diffuse galaxies are enormous, ghostly systems that, despite being as large as the Milky Way in terms of size, barely contain any stars at all. When first discovered, they seemed almost like a trick of the telescope, too faint and too spread out to be real. At first glance, an ultra-diffuse galaxy might not seem very exciting. Observing one is like trying to see a faint smudge against the black of space, with a few scattered points of light barely hinting at its true size. Their low surface brightness makes them extremely difficult to detect, which is why they remained hidden from astronomers for so long, despite their huge extent. In fact, it was only thanks to sensitive surveys and careful searches through deep sky images that they began to be recognized around the mid-2010s. Unlike the dwarf galaxies that had already been well known, small collections of stars orbiting larger galaxies, ultra-diffuse galaxies have a strange combination of properties. Their mass in stars is incredibly low, but their sizes are huge. If you were to overlay one on top of the Milky Way, the edges would nearly match. Yet where the Milky Way has hundreds of billions of stars, an ultra-diffuse galaxy might have only a few million, or even fewer. Despite their sparse star content, ultra-diffuse galaxies often act as though they are much heavier than they appear. When astronomers measure their motions by studying how fast their few visible stars move, they find that the speeds are higher than expected if only visible matter were present. The only explanation that fits is that these galaxies are packed with dark matter. In many ultra-diffuse galaxies, dark matter appears to dominate to an extreme degree. Some estimates suggest that for every bit of normal matter we can see, there could be hundreds or even thousands of times more dark matter. This makes them some of the most dark matter-heavy structures known, relative to their visible components. Their cores, in particular, seem to be surrounded by deep, massive halos of dark matter, holding them together despite their fragile appearance. One famous example that drew attention was DF44, located in the Coma cluster. When astronomers looked closer at DF44, they found it to be almost entirely made of dark matter. Its few stars were spread out across a huge area, giving it the visual appearance of a puff of smoke drifting in the cosmic wind. Yet it behaved as though it had a mass comparable to a galaxy many times brighter. Normally, a large halo of dark matter would gather gas, which would then collapse to form stars. But in these ultra-diffuse galaxies, something disrupted that process. Either the gas never cooled enough to make stars, or the stars that did form were stripped away by violent interactions with other galaxies or tidal forces inside clusters. Some theories suggest that supernova explosions early in their histories might have blown away much of the gas needed for star formation. Others propose that they are failed galaxies, objects that had enough dark matter to grow big but never enough material to light up. Not all ultra-diffuse galaxies fit the same pattern, though. Some, surprisingly, seem to have much less dark matter than expected. A handful of discoveries have found ultra-diffuse galaxies, where stars move more slowly than predicted, suggesting a lighter, almost ghost-like core without the heavy dark matter halo. These cases are rare and still debated, but they hint that ultra-diffuse galaxies might not be a single type of object. Instead, they could represent multiple paths through galaxy evolution, all leading to the same faint, scattered appearance. In the largest galaxy clusters, ultra-diffuse galaxies are often found in large numbers, like a mist of invisible giants drifting through the cluster's gravitational well. Their presence in clusters also supports the idea that tidal forces, the gravitational pull of many neighboring galaxies, could be responsible for their unusual shapes and sizes. Over time, the interactions might have stretched them out, pulled away stars, and left behind the vast, dim structures we observe today. Their low brightness means that even powerful telescopes struggle to gather enough light to analyze them in detail. Special techniques, such as stacking images or using extremely long exposure times, are often needed to tease out their properties. Because they are so dominated by dark matter, they serve as a natural testing ground for studying its properties. By watching how their stars move and how the galaxies interact with their environments, astronomers can test theories about whether dark matter behaves exactly like a perfect invisible substance, or if it might have tiny interactions that show up only in special conditions. A galaxy as wide as the Milky Way can be so faint that it nearly vanishes from view, while a small, bright galaxy can outshine everything around it. Brightness and mass are not always linked, and nature finds many ways to arrange matter and light in unexpected patterns. As deeper sky surveys come online, astronomers expect to find many more ultra-diffuse galaxies. Some may turn out to be even larger and more massive than those already discovered. Others might reveal themselves as remnants of violent collisions, the scattered bones of galaxies that once burned brightly but were torn apart by forces beyond their control. The missing baryon problem: where did half of ordinary matter vanish? By measuring light from stars and galaxies, counting their number, and applying what was known about the behavior of matter, it seemed possible for scientists to map out how much ordinary material, protons, neutrons, and electrons, was present across the cosmos. But over time, a strange problem emerged. When adding up all the visible matter, it turned out to be only about half of what should exist according to early universe measurements. This is known as the missing baryon problem, and it has led researchers to look beyond the bright stars and shining galaxies to find where all the lost matter is hiding. Baryons are the particles that make up ordinary matter. After the Big Bang, models of how the universe evolved, combined with precise measurements of the cosmic microwave background, or CMB radiation, predicted a certain density of baryons. That density, however, did not match what astronomers actually saw when looking at the universe billions of years later. When they counted the baryons tied up in stars, planets, and interstellar gas, they found only about half the amount that should be there. This was different from the well-known mystery of dark matter. Dark matter is something else entirely. The missing baryon problem deals with regular matter, the stuff that ought to be shining or detectable through its effects on light, but simply wasn't being seen. At first, the idea that half the ordinary matter could simply vanish seemed unlikely. Some researchers wondered if early measurements might have been wrong. But as instruments improved and observations became more accurate, confidence grew that the early estimates were correct. The missing matter was real. It just wasn't where anyone thought to look. Attention turned toward the spaces between galaxies and galaxy clusters, areas often overlooked because they are incredibly faint. Scientists proposed that much of the missing baryonic matter might not be in galaxies at all, but scattered throughout the vast cosmic web, the large-scale structure of the universe made up of filaments, voids, and sheets of matter. One leading idea is that the missing baryons exist in a state known as the warm-hot intergalactic medium, or WIM. The WIM is thought to be a diffuse network of gas that is too thin to see directly with optical telescopes and too cool to emit much X-ray light. It would be hot enough, between 100,000 and 10 million degrees Kelvin, to make atoms lose electrons, forming a plasma, but spread out so thinly that it remains nearly invisible across vast distances. Because it does not shine brightly, scientists have to look for its effects in indirect ways. One method involves looking at how the light from distant quasars, bright beacons powered by supermassive black holes, changes as it passes through the intergalactic medium. As the light travels across billions of light years, it passes through patches of gas, leaving behind subtle fingerprints in the form of absorption lines. These lines appear at very specific wavelengths, where certain elements like oxygen or hydrogen absorb light. By stacking observations from many quasars and carefully analyzing the absorption lines, astronomers have been able to piece together a picture of the WIM. They found evidence of thin, hot gas stretched along the filaments connecting galaxies and clusters, just where the cosmic web models suggested it would be. It's not enough to detect in any single spot easily, but over many observations, the presence of the missing baryons starts to become clear. In 2018, a breakthrough came when researchers used a clever technique involving FRBs. As these radio bursts traveled through space, they were slowed slightly by the free electrons in the plasma of the WIM. By measuring the delay between different frequencies of the radio waves, scientists could estimate how much ordinary matter the bursts had traveled through. The results showed that the missing baryons could indeed be accounted for by the thin, spread-out plasma between galaxies. Even though the mystery of where the missing baryons are hiding seems close to being solved, many details remain. For instance, the exact temperature, distribution, and structure of the WIM are still being worked out. Some sections of the cosmic web might be denser and hotter than others, leading to small, localized patches that are easier or harder to detect, depending on where astronomers look. The missing baryon problem teaches an important lesson about the universe. Much of what exists can be almost invisible if it is spread thinly enough or heated to the right conditions. It challenges the natural assumption that the most obvious and brightest parts of the cosmos, stars, galaxies, clusters, are where most of the matter should be. Instead, the universe seems to prefer tucking much of its ordinary matter into hard-to-see regions, stretching between the islands of galaxies that float like small lights in a deep, dark ocean. Gas flowing along the cosmic web may feed into galaxies, providing the raw material needed to form new stars. Likewise, energy and material blasted out of galaxies by supernova explosions or supermassive black holes can push baryons back into the intergalactic medium. Understanding the WIM is not just about solving a counting problem. It's also about understanding galaxies on a more holistic level. X-ray telescopes like Athena, planned by the European Space Agency, aim to map the hot gas more precisely. Radio observations of FRBs will become more common and refined, giving better measurements of the cosmic web's plasma. Together, these efforts should fill in the picture of how baryons are distributed across the universe and how they move over cosmic time. Without accounting for all the baryons, models of cosmic evolution, star formation, and galaxy behavior would remain incomplete. Polar ring galaxies, orthogonal rings that defy formation theories. Polar ring galaxies are rare objects that look like cosmic sculptures, hosting a bright, flat disk of stars and gas surrounded by a wide ring that orbits at a steep right angle, forming an almost perfect cross in space. This odd three-dimensional structure stands apart from the usual spiral, elliptical, and irregular galaxies. At first glance, a polar ring galaxy appears almost like two galaxies caught in a frozen dance. A central body spinning one way, and a separate ring of stars and gas spinning another. But the ring is not a separate galaxy caught in orbit. It is material, stars, dust, and gas, that has settled into a stable path, looping around the host galaxy's poles. Instead of lying flat like most galactic features, the ring wraps around vertically, as if tracing the halo of the galaxy rather than its plane. One of the best-known examples of this phenomenon is NGC 4650A, located about 130 million light-years away in the Centaurus constellation. When astronomers first observed it in detail, they quickly realized that its structure did not fit any normal category. Its central body looked somewhat like a lenticular galaxy, a kind of smooth disk lacking spiral arms. But the large luminous ring that swept around it did not match the orientation of the central disk. It was tilted almost at 90 degrees, forming a brilliant cross-like figure against the darkness. For every tens of thousands of normal galaxies, there may be only a handful with such an arrangement. This scarcity hints at a special set of conditions required for their creation. But what exactly causes a galaxy to form a polar ring remains an open question. A leading theory is that polar rings form through galactic mergers or close encounters. In this model, a smaller galaxy passes very near a larger one or collides with it at just the right angle. During the interaction, gravitational forces pull streams of gas and stars away from the smaller galaxy. Some of this material falls into a ring around the larger galaxy, settling into an orbit perpendicular to the main disk. Over time, the ring stabilizes and forms new stars, making it shine brightly in optical light. Another idea is that a polar ring can form through the slow accretion of material from intergalactic space. A galaxy moving through a filament of cosmic gas might gradually pull in material that happens to fall in along a polar orbit. Though this process would be slower and less violent than a merger, it would still require a careful balance of motion and gravitational influence to build a full ring. Whatever the exact cause, creating a polar ring seems to require fine-tuned conditions. If the collision or accretion were too violent, the galaxy could be torn apart completely, ending up as a chaotic, irregular galaxy. If it were too mild, the material might simply spiral into the galaxy's main disk, disappearing without forming a distinct ring. The polar rings we see must be the result of a delicate dance, too rough or too soft, and the structure would never exist. Because the ring orbits at right angles to the main disk, it moves in a different gravitational plane, offering a rare chance to study a galaxy's three-dimensional mass distribution. By measuring the speed and shape of the ring's motion, astronomers can map the shape of the dark matter halo that surrounds the galaxy. Some studies have suggested that polar rings are only stable if the host galaxy's dark matter halo is roughly spherical rather than flattened like the visible disk. Others propose that a slightly elongated or triaxial halo could help keep the ring in place. Besides their importance for dark matter studies, polar rings also reveal much about the flow of gas and the process of star formation under unusual conditions. In many polar ring galaxies, the ring is rich in hydrogen gas, the raw material for new stars. Bright patches within the rings show where stars are forming actively, glowing with the light of young, hot stars. In some cases, the star formation in the ring can even rival or exceed that in the central galaxy. The central galaxy may host older, redder stars, while the polar ring is populated with younger, bluer ones. This difference supports the idea that the ring material was acquired later in the galaxy's life, rather than being an original part of its formation. Some polar ring galaxies also exhibit faint connections or bridges to other galaxies nearby, suggesting that recent interactions may still be shaping their structure. In other cases, no nearby companions can be found, making it more difficult to trace the ring's origin. This mystery deepens when considering that some polar rings seem exceptionally stable, lasting for billions of years without breaking apart. This stability hints at an intricate balance of gravitational forces, mass distribution, and orbital motion. Traditional models often picture galaxies forming in relatively simple ways, either collapsing clouds of gas forming rotating disks or merging bodies combining to make larger structures. Polar rings suggest that more complex and finely tuned processes can occur, creating long-lasting, exotic structures that defy easy classification. Detailed simulations, powered by powerful supercomputers, are helping scientists model how polar rings might form, evolve, and interact with their host galaxies over cosmic time. Extended ultraviolet disks, star formation where it shouldn't happen. When looking at most spiral galaxies through an optical telescope, the stars seem to follow a certain order. Bright arms spiral out from a central bulge, tapering off into fainter and fainter starlight until the galaxy fades into the darkness. For a long time, astronomers believed that beyond a certain point, star formation simply stopped. The gas density in the outer regions of a galaxy would be too low, the environment too quiet and stable for new stars to form. But when researchers began looking at galaxies with ultraviolet telescopes, they found strange, ghostly disks of ultraviolet light stretching far beyond the visible boundaries of many galaxies. These are the extended ultraviolet disks, or XUV disks. Ultraviolet light is a strong signature of young, hot stars. Massive stars live fast and die young, shining brightly in UV for only a few million years before ending their lives in supernova explosions. So when a galaxy shows UV light far beyond its visible edges, it is a signal that new stars are being born in its outermost regions. These extended disks are surprising because traditional models said that there should not be enough gas in these parts of the galaxy to form stars. The conditions were thought to be too sparse, too diffuse, lacking the critical density needed to trigger the collapse of gas clouds into newborn stars. The discovery of XUV disks began with the Galaxy Evolution Explorer, or GALEX, a space telescope launched in 2003 that surveyed the sky in ultraviolet wavelengths. As GALEX observed hundreds of nearby galaxies, astronomers started noticing a pattern. Many spirals showed faint, sprawling UV structures extending 2, 3, or even 4 times further than their optical boundaries. In some cases, entire rings of UV light encircled galaxies like halos. In others, patchy clusters dotted the outskirts like islands in a dark sea. One early and well-studied example was the galaxy M83, the southern pinwheel galaxy. In visible light, M83 looks like a classic spiral with bright arms and a compact center. But in ultraviolet, GALEX revealed a sprawling network of star-forming regions far beyond where anyone expected them to be. Other galaxies, like NGC 4625 and NGC 1512, showed similar structures. It quickly became clear that extended UV disks were not rare, but rather a widespread phenomenon that had simply been hidden from view until new tools were available. The presence of star formation so far from the center of galaxies raised several important questions. First, how did the gas get there? And second, how could stars form in an environment that seemed too thin and empty to support the process? In many cases, the gas in the outer disks is made up of atomic hydrogen, detected through radio observations. These outer reservoirs of gas are much more diffuse than the dense molecular clouds found in the inner galaxy. In normal circumstances, gas needs to reach a certain threshold density before gravity can overcome pressure and trigger collapse into stars. But in the outer disks, the densities are much lower than expected for star formation. Yet somehow, it still happens. One possible explanation is that local events create pockets of higher density. Spiral density waves, the same mechanisms that organize stars into arms closer to the galactic center, might extend weakly into the outskirts, gently compressing gas in certain regions. Another idea is that minor mergers, small dwarf galaxies falling into the larger galaxy, disturb the outer gas enough to trigger new star formation. Some galaxies with extended UV disks show signs of past interactions or faint tidal streams, suggesting that external influences could play a role. There is also evidence that some outer star formation could be self-propagating. A small group of young, massive stars could trigger further star formation around them through their strong stellar winds and radiation pressure. This feedback might carve new clumps out of the diffuse gas, creating chains of new stars even in a low-density environment. The stars forming in these extended disks are not the massive clusters found in galactic cores or spiral arms. Instead, they tend to form in small associations, lightweight groups with relatively few massive stars. Because the gas is so thin and the star formation rates are low, these outer disks build up very slowly. But over cosmic time, they can significantly contribute to the growth of a galaxy's size and mass. Traditional models of galaxy formation emphasized rapid star formation early in a galaxy's life, followed by a slow aging as gas was used up. But XUV disks show that even mature galaxies continue to build new stars at their edges, adding layers like tree rings. This process, sometimes called galactic disk inside-out growth, changes our understanding of how galaxies evolve over billions of years. Different types of extended UV disks have been identified based on their structure and brightness. Type 1 XUV disks have bright, structured outer star formation, often organized into rings or arms that can be easily traced. Type 2 XUV disks are more diffuse and irregular, with faint patches of UV light scattered unevenly across the outskirts. These differences may reflect different formation histories or different external influences acting on the galaxies. Some galaxies show enormous UV disks stretching hundreds of thousands of light years. Others have much more modest extensions. In all cases, though, the common thread is that star formation is taking place well beyond the regions where traditional models said it should be possible. Galaxies sit within larger halos of dark matter and are surrounded by the intergalactic medium. Some theories suggest that cold gas streams from the cosmic web could slowly feed into galaxy outskirts, replenishing the gas supply and fueling extended star formation. If true, XUV disks could be direct evidence of galaxies sipping from the cosmic web. Observations across multiple wavelengths are helping to build a more complete picture. In addition to ultraviolet light from young stars, astronomers map the atomic gas with radio telescopes and search for faint signs of molecular gas with sensitive millimeter wave observatories. In some cases, deep optical imaging reveals that the UV regions coincide with very faint starlight, showing that older populations of stars may also be building up over time. The study of extended UV disks suggests that star formation is more resilient than previously thought, able to proceed even in environments that seem marginal. It highlights the importance of low-density gas reservoirs in shaping the future of galaxies. And it reminds us that our view of the universe is always limited by the tools we use. When new wavelengths are explored, hidden structures emerge. Starbirth is not confined to the bright, crowded regions. It reaches outward into the quiet, thin edges of galaxies, pushing the boundaries of where life and light can emerge. Fermi bubbles, gamma-ray cavities towering over the Milky Way. High above and below the center of the Milky Way, stretching tens of thousands of light years into space, are two giant structures called the Fermi bubbles. These bubbles, only discovered recently in 2010 through observations made by the Fermi Gamma-Ray Space Telescope, glow brightly in gamma rays, the highest energy form of light. The Fermi bubbles extend about 25,000 light-years above and below the galactic center, towering over the relatively thin disk of the Milky Way. If we could see them with our eyes, they would dominate the night sky, stretching across as much of the sky as dozens of full moons laid side by side. But because they radiate in gamma rays, a part of the spectrum far outside human vision, they remained hidden until the right instruments came along. Gamma rays are produced in some of the most extreme environments in the universe. They can come from exploding stars, colliding neutron stars, or matter swirling around black holes. So when the Fermi telescope revealed the presence of these twin bubbles, it was clear that something very energetic had created them. A leading idea is that the Fermi bubbles are the leftover footprints of a past outburst from Sagittarius A star. Today, this black hole is relatively quiet compared to the active giants at the hearts of other galaxies. But there is strong evidence that Sagittarius A star was once much more active. If the black hole had, at some point in the past few million years, swallowed a large amount of gas, it could have launched powerful jets of particles out into space, inflating the bubbles we now see. Another possibility is that the Fermi bubbles were created by a massive burst of star formation near the galactic center. In what's known as a starburst event, rapid and intense formation of massive stars can flood a region with energy. When these stars die as supernovae, they can drive enormous winds of hot gas and energetic particles outward, possibly creating large structures like the bubbles. In this case, the bubbles would be like cosmic chimneys, venting energy from the crowded center of the galaxy into its halo. Evidence supporting both ideas has been found, but neither fully explains all the features of the Fermi bubbles. For instance, the edges of the bubbles are surprisingly sharp. There's a clear boundary where the gamma-ray glow ends, rather than a gradual fading into the surrounding space. This suggests that the energy source was sudden and violent, rather than a slow and steady process. The symmetry of the two bubbles, one above and one below the galactic plane, also hints at an organized central origin, like jets from a black hole rather than random star formation events. Observations in X-rays, radio waves, and even microwaves have found corresponding structures aligned with the Fermi bubbles. One feature, known as the microwave haze, lines up closely with the lower energy side of the bubble's emission. This suggests that whatever event created the Fermi bubbles also energized particles across a broad range of energies. The particles inside the bubbles seem to be mainly electrons and positrons moving close to the speed of light. These particles emit gamma rays through a process called inverse Compton scattering, where high-speed electrons slam into lower energy photons, such as those from the CMB, and boost them up to gamma-ray energies. This mechanism helps explain the smooth glow of the bubbles without needing a huge number of distinct point sources. What remains puzzling is how the bubbles maintain their structure. The Milky Way is not a still environment. It is filled with magnetic fields, cosmic rays, and turbulent clouds of gas. Over millions of years, one might expect such structures to dissipate, lose their shape, or get shredded by galactic winds. Yet the Fermi bubbles remain coherent, with their sharp edges intact. This suggests that they are either relatively young, only a few million years old, or that some mechanism is keeping them stable. Some models suggest that magnetic fields wrapping around the bubbles could help preserve their shape, acting like a kind of invisible cocoon. The smooth, symmetric glow of the bubbles has led a few scientists to suggest that dark matter interactions might contribute to the observed emission. However, this idea remains speculative, and most evidence still points to a more conventional origin involving black holes or starbursts. Other galaxies show signs of giant outflows and bubbles, often associated with active black holes or intense periods of star formation. By studying the Fermi bubbles up close, astronomers can better understand similar processes happening in galaxies millions or billions of light-years away. One aspect that researchers are looking into is the possible motion inside the bubbles. If particles are moving within the bubbles, they might leave subtle imprints on the microwave or radio signals we observe. Studying these motions could provide clues about how the bubbles were inflated and how they interact with the surrounding galactic halo. These silent towers of gamma rays are ghostly echoes of past events, stretching across the galaxy like invisible cosmic scars. Through these bubbles, we catch a glimpse of one of the myriad forces that have shaped not only our own galaxy, but countless others scattered across the universe. Anomalous microwave emission, the Milky Way's spinning dust glow. For years, astronomers searching the sky with sensitive microwave detectors kept noticing something strange. There was a signal that didn't quite fit what they expected. It wasn't coming from ordinary stars, and it wasn't the well-known afterglow of the Big Bang either. This mysterious glow became known as anomalous microwave emission, or AME. The discovery of AME happened slowly, starting in the 1990s, when scientists were trying to study the CMB. To see the CMB clearly, astronomers needed to remove all the foreground signals coming from our own galaxy, like the normal microwave glow from warm dust, or electrons spiraling in magnetic fields. As they peeled away these expected layers, something unexpected remained. It was a faint but widespread glow that didn't match any known source. At first, there was confusion about what could be causing it. The usual suspects, like warm interstellar dust grains, didn't seem to explain it. Dust typically emits infrared light, not microwaves, and when it does emit at longer wavelengths, it follows predictable patterns based on its temperature. But this strange emission was strongest in a very specific range of microwaves, peaking around 20 to 40 gigahertz. It also appeared to trace the same regions of the galaxy that were rich in cold dust, but the temperatures didn't add up. One of the leading ideas that developed was that the anomalous emission might come from tiny, rapidly spinning dust grains. These grains are much smaller than a typical speck of dust you would find in your home. They are more like large molecules, made up of a few dozen to a few hundred atoms. Astronomers call them very small grains or nanoparticles. These grains can spin at astonishing speeds, billions of times per second, because of various physical effects. In the interstellar medium, these tiny dust grains are constantly bombarded by UV light from stars, by stray electrons, and by ions. Each collision or flash of light can give a dust grain a tiny nudge, setting it spinning faster and faster. In some cases, the grains can carry electric charges. When a spinning charged object moves, it emits electromagnetic radiation. If these tiny grains spin fast enough, they could naturally emit microwaves. This idea, known as the spinning dust model, offered a new way to understand AME. It suggested that the Milky Way's mysterious microwave glow was not from hot dust or from electrons spiraling in magnetic fields, but from the rotational energy of these incredibly tiny particles. It was an elegant solution that tied together ideas from physics, chemistry, and astronomy. Still, proving this model was not simple. The properties of interstellar dust are complex and not fully understood. The interstellar medium is a messy environment, filled with magnetic fields, radiation, shock waves from supernova, and all sorts of chemical reactions. Predicting exactly how dust grains behave in this environment is difficult. Moreover, no one had ever directly observed an individual spinning dust grain emitting microwaves. All the evidence had to come from large-scale observations and careful modeling. Over the next 2 decades, astronomers used a variety of instruments to map the microwave sky in more detail. Observatories like WMAP and Planck provided clearer and sharper images of AME, confirming that it was a real and widespread phenomenon. These maps showed that AME was strongest in regions with lots of cold dust, but relatively little free ionized gas, which fit the spinning dust picture. Researchers also found that AME was polarized very weakly, another hint that it came from randomly oriented spinning particles rather than neatly aligned dust grains. Other possible explanations, like magnetic dipole emission from dust grains made of magnetic materials, were considered, but none matched the data as well as spinning dust. Today, while scientists still debate some details, spinning dust remains the leading theory behind anomalous microwave emission. For a long time, astronomers thought of space between the stars as mostly empty, with a thin sprinkle of gas and dust. But the discovery of AME shows that even the tiniest bits of matter, grains smaller than a virus, can have major effects on the galaxy's appearance at certain wavelengths. It also shows that processes happening on the scale of molecules and atoms can shape what we see on scales larger than whole star systems. Because it contaminates the microwave sky, astronomers trying to study the early universe have to carefully remove its signal. If they don't, it could introduce errors into maps of the CMB, leading to incorrect conclusions about the history and structure of the universe. So understanding AME is essential for one of the biggest scientific efforts of our time. Scientists are now looking for signs of AME in other galaxies. If spinning dust is a universal phenomenon, it should occur wherever there is a mix of tiny dust grains and energetic processes to spin them up. Some hints of AME have been found in nearby galaxies, though detecting it is challenging because the signals are so faint. Finding AME in other galaxies would not only confirm our models, but also open a new window for studying the properties of interstellar dust in different environments. In recent years, astronomers have started to wonder whether there might be more than one type of AME. Perhaps different kinds of dust grains contribute at different frequencies. Some theoretical models suggest that grains made of particular materials, like polycyclic aromatic hydrocarbons, might be especially important for producing AME. Others propose that a whole family of spinning particles, each with different sizes and shapes, could be responsible, creating a more complex microwave glow than a single population would. Laboratory studies of cosmic dust analogues are helping to test these ideas. By creating tiny dust grains under controlled conditions and spinning them using electric fields or light, researchers can measure their emissions directly. These experiments are still in early stages, but they offer the exciting possibility of linking real-world laboratory physics to the mysteries of the Milky Way. The upcoming CMBS-4 project and ground-based arrays, like the Simons Observatory, will be able to map AME in even finer detail. This will help answer questions about how the spinning dust changes in different parts of the galaxy, whether near dense molecular clouds, empty regions of the galactic halo, or sites of recent star formation. Diffuse interstellar bands, hundreds of unidentified spectral features. In the early 20th century, astronomers studying the light from distant stars noticed that when they passed the starlight through a spectroscope, breaking it into its rainbow of colors, they saw dark bands where some of the light was missing. These dark marks weren't from the stars themselves, nor were they from Earth's atmosphere. They came from somewhere in the vast spaces between the stars. Over time, hundreds of these dark features were catalogued. They came to be known as the diffuse interstellar bands, or DIBs. At first, the discovery was just a curiosity. Astronomers knew that gas and dust between stars could absorb or scatter light. They had already identified many sharp lines caused by elements like sodium and calcium in interstellar clouds. But the DIBs were different. They were broader and fuzzier than the crisp absorption lines of simple atoms. They also appeared at strange wavelengths that didn't match any known atoms or molecules. Most importantly, they seemed stubbornly resistant to identification. For more than a century now, the origin of the diffuse interstellar bands has remained one of the big unsolved mysteries of astronomy. Hundreds of distinct DIBs have been found, spread from the near ultraviolet part of the spectrum into the near infrared. Some are strong and obvious, while others are faint and subtle. No matter how carefully scientists have measured them, most of the carriers, the actual particles or molecules responsible for absorbing the light, remain unknown. One thing is clear: whatever is causing the DIBs is part of the interstellar medium. When astronomers study the light from stars behind dusty clouds, they see the DIBs grow stronger. In areas with little dust, the bands are weaker. This suggests that the same regions of space filled with gas and dust also contain the mysterious carriers of the DIBs. Early on, some thought they might be simple molecules, like carbon chains or small bits of soot. Others suggested more exotic possibilities, such as ionized molecules, very large organic compounds, or even fragments of tiny interstellar grains. One leading theory today is that many DIBs are caused by complex carbon-based molecules called polycyclic aromatic hydrocarbons, or PAHs. These molecules are made of rings of carbon atoms bonded together, often with hydrogen atoms attached. PAHs are common in space and are thought to form when stars die and throw their outer layers into the galaxy. They are tough, able to survive in the harsh conditions between the stars. When bombarded by ultraviolet light, they can absorb certain wavelengths, possibly creating some of the DIBs. Another strong candidate is a class of molecules known as fullerenes. These are cage-like structures made entirely of carbon atoms, like tiny soccer balls or tubes. Fullerenes, such as the famous C60 molecule, have been found in space, and they have interesting absorption properties that could explain some DIB features. In fact, in 2015, researchers finally identified two DIBs with specific carriers, charged versions of the C60 fullerene, known as C60+. This was a major breakthrough because it proved that at least some DIBs come from large carbon-based molecules. However, it also showed just how difficult the task is. It took precise laboratory measurements and careful astronomical observations to make the match. And C60+ explains only 2 of the hundreds of known DIBs. One reason it's so hard to identify the DIB carriers is the nature of space itself. The interstellar medium is cold, with temperatures often just a few tens of degrees above absolute zero. Molecules behave differently at such low temperatures. They rotate and vibrate in slow, specific ways that can shift the wavelengths where they absorb light. Additionally, space is filled with ultraviolet radiation that can strip electrons from atoms and molecules, ionizing them and changing their absorption properties. To complicate things even more, DIBs often overlap or blend into each other. Some are wide and shallow, while others are narrow and deep. This makes it hard to tell whether a single DIB comes from one kind of molecule or a mix of several. It's like trying to hear a single musical instrument in a symphony where dozens are playing at once. Scientists also have to rely on laboratory experiments to identify possible carriers. They create molecules on Earth, chill them to space-like temperatures, and measure how they absorb light. Then they compare these patterns to the DIBs observed in starlight. But not every molecule found in the lab necessarily exists in space. And some molecules that might exist in space are difficult to create under Earth conditions. Despite the challenges, the study of DIBs has taught astronomers a lot about the chemistry of space. It has revealed that the interstellar medium is filled with rich, complex organic chemistry. It has shown that space is a place where large, carbon-rich molecules can form, survive, and interact with starlight. There are patterns in the DIBs that suggest some order behind the chaos. For example, stronger DIBs tend to appear in regions where there is more dust extinction, meaning more starlight is blocked by dust. Some DIBs are stronger in areas exposed to harsher radiation, while others are more common in sheltered regions. This hints that different carriers respond differently to their environments, providing clues about their chemical nature. The distribution of DIBs also gives astronomers a tool for mapping the structure of the Milky Way. Because DIBs are associated with interstellar clouds, they can act as tracers for the dusty, gas-rich regions between stars. In recent years, large surveys using powerful telescopes have begun to map DIB strength across the sky, offering new views of the galaxy's skeleton of gas and dust. Astronomers have also detected DIBs in other galaxies. Observations of nearby galaxies like the Large and Small Magellanic Clouds, as well as more distant starburst galaxies, show that DIBs are not unique to our home. However, the strength and patterns of the DIBs can differ from one galaxy to another, suggesting that local conditions, like the strength of the ultraviolet radiation field or the metallicity of the environment, affect the carriers. One of the most exciting possibilities is that solving the DIB mystery could open a window into the origins of complex organic molecules in space. Since carbon-rich molecules are essential for life as we know it, understanding how they form and survive in the harsh environments between the stars could offer clues about how the ingredients for life are spread across the galaxy. Even if the DIBs are not directly related to the chemistry of life, they are still an extraordinary example of nature's complexity. They show that even after centuries of studying the stars, the universe still holds deep secrets. The flyby anomaly, spacecraft gaining speed unexpectedly around planets. In the precise world of spaceflight, where every meter and second counts, spacecraft navigation relies on a deep understanding of gravity, motion, and the laws of physics. Mission planners use these laws to predict exactly where a spacecraft will be and how fast it will be moving. When a probe passes by a planet, engineers use a technique called a gravitational assist, or flyby, to steal a little momentum from the planet's orbit around the Sun. It's a clever and well-tested method that lets spacecraft reach distant worlds without using large amounts of fuel. But beginning in the 1990s, scientists noticed something strange during some of these planetary flybys. Spacecraft were gaining or losing tiny amounts of speed, small but measurable changes that didn't fit with the equations. This curious effect became known as the flyby anomaly. It first grabbed attention in 1990, during the Earth flyby of NASA's Galileo spacecraft. Galileo was on its way to Jupiter, and engineers expected it to gain a precise amount of speed as it swung around Earth. Instead, when they checked the data, they found that Galileo had picked up a little extra velocity, about 3.9 millimeters per second more than predicted. This might sound tiny, and in everyday life it would be invisible. But in space navigation, it was a noticeable and puzzling error. At first, engineers wondered if it was a mistake. Maybe there was an error in the tracking systems, or some unexpected thrust from the spacecraft itself. But as more flybys happened over the next few years, the pattern continued. The Near spacecraft, on its way to an asteroid, showed a similar unexpected speed increase after its Earth flyby in 1998. So did Rosetta in 2005. And while some missions like Cassini showed no anomaly, the effect was real enough and consistent enough to raise serious questions. Scientists began digging into every detail they could think of. They rechecked Earth's shape and gravity field. They looked for hidden forces, like air resistance from the very outer layers of the atmosphere. They examined radiation pressure from the sun and the spacecraft's own heat emissions. They even considered whether the way spacecraft antennas radiate energy could produce a recoil, like a very small push in the opposite direction. None of the usual suspects could fully explain the flyby anomaly. The spacecraft seemed to be obeying Newton's laws during most of their orbits, but something odd happened during the moments when they were closest to Earth, where their paths curved sharply through the planet's gravity well. And it wasn't a random error. Some early studies suggested that the size of the speed change depended on the spacecraft's approach angle relative to Earth's equator. This hint led some researchers to wonder if the anomaly could be tied to the Earth's rotation. The Earth spins on its axis, carrying everything on its surface around at hundreds of meters per second. In theory, if a spacecraft passed by in just the right way, it might interact somehow with the moving mass of the planet, picking up a little extra energy. But in our current understanding of physics, including Einstein's theory of relativity, the effects of Earth's rotation on space travel are well understood and accounted for. There was no clear reason why it should produce the unexpected changes seen. Some proposed that maybe gravity itself behaves differently near spinning objects, a concept called frame dragging, predicted by general relativity, but not strong enough, according to known models, to explain the flyby changes. A few even suggested that the anomaly might hint at new physics, something not yet included in our equations about motion and gravity. More cautious voices pointed out that the anomaly could still have more ordinary explanations, hidden in the messy real world rather than exotic theories. The geometry of the flybys was extremely complex, with spacecraft moving at many kilometers per second through rapidly changing gravitational fields. Tiny errors in how the tracking stations on Earth measured the spacecraft's Doppler shifts, the changes in the frequency of their radio signals, could add up to a small but noticeable velocity change. One of the difficulties in solving the flyby anomaly was that it didn't happen during every flyby. Some missions showed no unexpected changes at all. Others showed small positive boosts, while a few, like Rosetta's second Earth flyby, showed a slight loss of speed instead. This inconsistent behavior made it hard to pin down a single cause. Further complicating matters, the spacecraft themselves were all different. Different designs, different shapes, different communication systems, different orientations during the flyby. It was possible that something unique to each spacecraft's structure was playing a role, interacting with Earth's environment in unexpected ways. But there was no clear pattern tying the anomaly to a specific kind of spacecraft or hardware. Efforts to simulate flybys in computer models produced results that matched the expected trajectories without needing to add in a mysterious extra force. Yet, the tracking data, the real signals received from the spacecraft, showed that something subtle was happening during the real flybys. One of the most detailed studies suggested that the amount of the anomaly could be predicted based on the incoming and outgoing angles of the spacecraft relative to Earth's equator. If the approach and departure paths were symmetric, no anomaly was seen. If they were asymmetric, a small net speed change appeared. But even this model did not explain why the interaction would occur in the first place. Rosetta performed 3 Earth flybys on its way to its final destination, a comet. The first flyby showed an unexpected speed increase, the second showed almost nothing, and the third showed a small decrease. Each time, the conditions were slightly different, and no simple rule fit all 3 results. By the late 2010s, interest in the flyby anomaly had cooled somewhat, partly because no new flybys showed clear, consistent effects, and partly because other mysteries, like the Pioneer anomaly, had found more conventional explanations over time. With improved tracking techniques and better understanding of spacecraft behavior, many in the space science community began to suspect that the flyby anomaly might eventually be explained without needing new physics. Still, the mystery is not officially solved. No consensus exists on the cause, and no fully accepted model accounts for all the data. As new spacecraft head out into the solar system, careful monitoring during their Earth flybys could either shed more light on the puzzle or show that it was a quirk of past missions and past measurement methods. For now, every flyby is a quiet test, a moment when spacecraft and planet dance together, and observers on Earth watch closely, asking whether the old rules will be enough, or whether, once again, something unexpected will slip through the cracks. The Hubble tension, conflicting measures of cosmic expansion. The story of the expanding universe began with Edwin Hubble's discovery in the 1920s that distant galaxies are moving away from us, and that their speed increases with distance. This relationship became known as Hubble's law, and the rate of expansion was defined by a number, the Hubble constant. For decades, measuring this constant more and more precisely became one of the central goals of cosmology. It was seen as a key to understanding the age, size, and fate of the universe. For much of the 20th century, estimates of the Hubble constant varied widely, but by the early 2000s, things seemed to be converging. Thanks to projects like the Hubble Space Telescope Key project, the number had narrowed to around 70 kilometers per second per megaparsec. That means that for every megaparsec, or about 3.26 million light-years, a galaxy appears to recede 70 kilometers per second faster. But in recent years, a new problem has appeared, and it refuses to go away. Measurements of the Hubble constant made using nearby objects, like Cepheid variable stars and supernovae, are not matching the measurements made using the CMB. The discrepancy is significant enough that many scientists now believe it could be a sign that something important is missing from our understanding of the universe. When scientists measure the Hubble constant using local methods, they start by finding standard candles, objects whose true brightness they know. Cepheid variable stars, for example, have a well-known relationship between how fast they pulse and how bright they are. By comparing their known brightness to how bright they appear from Earth, scientists can calculate how far away they are. Once distances are known, they can be compared to how fast those objects are moving away using the redshift of their light. This gives a direct measurement of the expansion rate in the nearby universe. Using this method, teams like SH0 led by Adam Rees have found a Hubble constant around 73 to 74 kilometers per second per megaparsec. On the other hand, the Planck satellite has mapped the CMB in extraordinary detail. By analyzing tiny fluctuations in temperature and density across the early universe, scientists can work out the conditions just a few 100,000 years after the Big Bang. They then feed those conditions into the standard model of cosmology, a model that includes dark matter, dark energy, and ordinary matter. From this, they can predict what the expansion rate should be today. Planck's measurements predict a Hubble constant of about 67.4 kilometers per second per megaparsec, notably lower than the local measurements. At first, scientists thought the tension might be due to systematic errors. Maybe something about the Cepheid stars or the way supernovae are calibrated was throwing off the local measurements. Or perhaps the assumptions built into the early universe model were wrong in subtle ways. Teams on both sides of the debate worked hard to rule out sources of error. They rechecked their calibrations, used different kinds of standard candles, like tip-of-the-red giant branch stars, and developed independent methods like strong gravitational lensing time delays and water mazes in nearby galaxies. These different approaches largely supported the original local measurement. Meanwhile, refinements to Planck's data analysis confirmed the lower early universe value. Instead of disappearing, the tension grew sharper. The difference between 67 and 74 might not sound huge, but the uncertainty in the measurements has become small enough that the gap now stands at over 5 sigma. In other words, there's less than a 1 in a million chance that the difference is just random noise. In science, 5 sigma is often treated as the gold standard for a discovery. The fact that the tension has crossed this threshold has led many scientists to wonder if it points to new physics beyond the standard model of cosmology. Several ideas have been proposed. One possibility is that something changed between the time the CMB was created and today. Maybe dark energy, the force causing the universe's expansion to accelerate, behaved differently in the past than it does now. Some models suggest that there could be a form of early dark energy that briefly influenced the universe's expansion soon after the Big Bang, altering the way the early fluctuations evolved into today's large-scale structure. If this energy faded away quickly, it might explain why early and late measurements don't agree. Another idea involves neutrinos, the ghostly particles that pass through matter almost undisturbed. The standard model includes 3 types of neutrinos, but what if there were a 4th, more massive kind, a sterile neutrino? Additional kinds of neutrinos could change how the early universe evolved, shifting the expected Hubble constant. There are also models involving modifications to gravity itself. Einstein's general relativity works extremely well on solar system scales and even across galaxies, but it has never been directly tested on the largest cosmic scales. Some researchers propose that gravity might behave slightly differently over vast distances or at different points in cosmic history, affecting the rate of expansion. None of these ideas have been confirmed. Each proposal must match not only the Hubble tension, but all other precise cosmological observations. Things like galaxy clustering, supernova distances, and the detailed shape of the CMB spectrum. It is a delicate balancing act. So far, no single new physics model has emerged as a clear winner. Meanwhile, the observational work continues. New surveys and measurements are trying to sharpen the Hubble constant even further. JWST, with its ability to observe Cepheid variables in distant galaxies more precisely, is adding new data. Gravitational wave astronomy also offers an additional tool. When 2 neutron stars merge, they emit both gravitational waves and light. By comparing the gravitational signal, which tells us about distance, to the light signal, which tells us about redshift, scientists can make an independent measurement of the Hubble constant. These standard sirens could help break the deadlock. Some researchers suggest that the tension itself might eventually fade as better data and better models narrow the gap. Maybe hidden systematics still lurk in the measurements. Maybe we are underestimating the complexity of local cosmic flows, like how the Milky Way moves relative to the surrounding cosmic web. Local structures could, in theory, bias our distance measurements if not properly accounted for. Others believe the Hubble tension is here to stay, a signpost pointing toward a deeper and more complex universe than we thought. In either case, it has already had a profound impact. Even in a field where models fit observations so well, explaining everything from the abundance of light elements to the formation of large-scale structures, there can still be cracks. And sometimes, it is the cracks that reveal new landscapes beyond. The Hubble tension has brought cosmologists into a new era of precision. Where once the Hubble constant was uncertain by a factor of 2, now it is measured to a few percent. Yet instead of convergence, the closer we look, the more disagreement we find. Whatever the final answer turns out to be, the effort to solve the Hubble tension is driving some of the most creative and careful work in modern astronomy. The lithium problem. According to our best understanding, the first few minutes of the universe's life were marked by an event called Big Bang nucleosynthesis. During this brief but critical period, the universe was hot and dense enough for nuclear reactions to occur. Protons and neutrons collided, forming the lightest elements, mostly hydrogen and helium, with tiny amounts of deuterium, helium-3, and lithium-7. The predictions made by Big Bang nucleosynthesis theory have been one of the major successes of cosmology. Measurements of the cosmic abundances of hydrogen, helium, and deuterium match the theory almost perfectly. But lithium tells a different story. When astronomers look at old stars, particularly those in the halo of the Milky Way, stars that formed early in the galaxy's history, they find far less lithium than the theory predicts. In fact, the amount of lithium observed is about 3 to 4 times lower than what should have been created in the Big Bang. This mismatch has become known as the cosmological lithium problem. The most reliable measurements of primordial lithium come from these ancient metal-poor stars. They are sometimes called population 2 stars. These stars have very little heavy elements, meaning they formed before generations of supernovae could enrich the galaxy with metals. They serve as fossil records, preserving the chemical conditions of the early universe. When astronomers examined the surfaces of these stars, they used spectroscopy to determine the abundance of different elements. The results show a consistent, relatively low amount of lithium, forming a plateau when plotted against metallicity, a feature now known as the Spite Plateau, named after Francois and Monique Spite, who discovered it in 1982. Initially, it was thought that perhaps the Big Bang theory was wrong in its predictions. But the success of deuterium and helium measurements suggested otherwise. Deuterium, in particular, is extremely sensitive to the density of baryons in the early universe. If the baryon density was significantly different, the deuterium abundance would not match observations. Yet it does, almost perfectly. This consistency means that the primordial production of light elements must have been close to the theoretical predictions. The problem, then, must lie elsewhere. One idea is that the stars themselves may have somehow altered their surface lithium over billions of years. Lithium is a fragile element. It can be destroyed at about 2.5 million degrees compared to the tens of millions needed for hydrogen fusion. If lithium sinks beneath the surface layers of a star and reaches hotter interior regions, it can be destroyed. Stellar models that include processes like diffusion, mixing, and turbulence suggest that some depletion of lithium should occur. However, even when these effects are taken into account, the models generally cannot account for the full discrepancy. Depletion may explain a factor of 2 or so, but not a factor of 3 or 4. Another possibility is that our understanding of nuclear reactions in the early universe might be incomplete. Big Bang nucleosynthesis depends on a network of nuclear reaction rates, how quickly protons and neutrons stick together to form heavier elements. If the rate of certain reactions involving lithium or its precursors were different than currently believed, it could shift the predicted amount of lithium. Experiments have been conducted to test key reactions, such as those involving helium-3 and deuterium, but so far no major errors have been found. Small adjustments can tweak the numbers a bit, but not enough to erase the problem. Some more exotic ideas have been proposed. One is that new physics beyond the standard model of particles could have played a role during Big Bang nucleosynthesis. For example, decaying particles from hypothetical early universe processes could have injected energy into the plasma, altering the nuclear reaction pathways. Some models suggest that unstable supersymmetric particles could have been around, modifying how lithium-7 was formed or destroyed. These highly speculative ideas provide a way to address the problem without disturbing the otherwise excellent agreement between theory and observation for other elements. There is also the curious case of lithium-6, a much rarer isotope of lithium. Some early measurements claim to detect higher than expected amounts of lithium-6 in old stars. If true, it would be very difficult to explain within the framework of standard Big Bang nucleosynthesis, because lithium-6 is much harder to produce than lithium-7. However, later studies cast doubt on these detections, suggesting that they might be artifacts of complex stellar atmospheres and line-broadening effects. Most astronomers today believe that the lithium-6 observations are too uncertain to be used as firm evidence for or against particular models. In the search for answers, astronomers have widened their net. They've studied lithium abundances not just in halo stars, but in globular clusters, dwarf galaxies orbiting the Milky Way, and even in the interstellar medium. These environments provide different conditions and histories, offering a broader view of how lithium behaves across cosmic time. Yet the fundamental problem remains. Everywhere we look, there seems to be less lithium than expected. New tools may help. The Gaia spacecraft, for example, has revolutionized our understanding of the Milky Way's structure and stellar populations by providing extremely precise distances to stars. With better distance measurements, we can refine models of star properties like temperature and gravity, leading to more accurate abundance measurements. Meanwhile, new telescopes promise to probe even fainter, older stars, potentially reaching closer to the true primordial conditions. Some researchers are exploring the possibility that the primordial lithium never made it into the stars we observe today. Perhaps early clouds of gas were chemically inhomogeneous, or processes like early star formation preferentially destroyed or sequestered lithium before the stars we see were born. This would shift the problem from nuclear physics to the complex dynamics of the first galaxies and stars. Despite many efforts, no single solution has emerged that neatly explains the lithium problem without creating new problems elsewhere. It remains one of the few major cracks in the otherwise successful theory of Big Bang nucleosynthesis. Like the Hubble tension, it reminds us that even our best models can still be incomplete. The universe often guards its secrets carefully, revealing just enough to guide us forward, but keeping some puzzles alive to fuel the next generation of discoveries. Which phenomenon has intrigued you the most? What other puzzles might still be out there? Sound off in the comments below, and if you enjoyed the video, consider leaving a like and subscribing. Thanks for watching,